Around 300 million years ago, our planet was home to breathtaking giants, not dinosaurs, but massive insects ruled the skies. These colossal creatures flourished in a world where atmospheric conditions and rich ecosystems enabled remarkable growth and evolution. As we unravel the mysteries of giant insects and their ecosystems, we will consider how climatic shifts and extinction events transformed life on Earth. Through this journey, we aim to deepen our understanding of biodiversity and the lasting cultural significance of these incredible creatures. Join us as we discover the wonders of Earth's distant past and its implications for our present and future. The prehistoric era of giant insects, often referred to as the Carboniferous period, unfolded around 350 to 300 million years ago. During this time, Earth's atmosphere was rich in oxygen, around 30%, compared to today's 21%. This high concentration supported the growth of massive arthropods, leading to the emergence of enormous insects. Dragonflies with wingspans of over 3 feet and millipedes that reached lengths of 8 feet are just a few of the astonishing examples from this era. Insects thrive in environments where oxygen levels are significantly increased, and the Carboniferous period provided the perfect conditions. Vast, swampy forests dotted the landscape, teeming with lush vegetation. These habitats not only offered ample food, but also suitable nesting sites. The abundant plants contributed to the formation of extensive coal deposits we still rely on today, showcasing the link between ancient ecosystems and our current energy sources. This remarkable time of insect giants fits into the broader timeline of Earth's history, following the Devonian period, known as the Age of Fishes. After the Carboniferous, Earth would transition into the Permian period, marked by significant evolutionary changes and eventually the largest mass extinction in history. The presence of these giant insects highlights a dynamic and ever-changing planet, wherein life adapted uniquely to the conditions of its time. The legacy of this prehistoric era remains with us today, as modern insects, while smaller, are descendants of those giants. Studying these colossal creatures helps scientists understand the evolutionary pathways that led to the diverse insect life forms we see now, providing insights into how environments shape life on Earth. The giant insects of the past remind us not just of the wonders of evolution, but also of the intricate relationships that persist in our ecosystems. During the prehistoric era, particularly during the Carboniferous period, insects thrived and grew to astonishing sizes, some even exceeding a wingspan of 2 feet. One primary reason for this remarkable growth was the increased levels of oxygen in the atmosphere, which were significantly higher than what we experience today. Oxygen levels soared to about 35% compared to the current 21%. This surplus allowed insects to efficiently transport oxygen through their bodies as they take in air through small openings in their exoskeleton, making it feasible for them to grow much larger without the limitations that exist in lower oxygen environments. Additionally, the absence of large vertebrate predators played a crucial role in the development of these giant insects. The Carboniferous period was characterized by a warm climate and lush vegetation, creating an ideal habitat for insects to flourish. With fewer threats, these insects could grow large and diversify without the competition and predation pressures that constrain their sizes today. As a result, they rapidly evolved into various forms, leading to an abundance of giant dragonflies, millipedes, and other fascinating species. The size of these prehistoric insects also indicates a significant evolutionary adaptation. Larger body sizes can confer advantages such as more efficient mating displays, better defense against smaller predators, and the ability to travel longer distances in search of food. These adaptations would have allowed them to dominate their ecological niches, making them successful survivors during their time. The combination of elevated oxygen levels, a lack of formidable predators, and significant evolutionary adaptations created a perfect environment for insects to reach sizes we can only imagine today. This period in Earth's history serves as a captivating reminder of how environmental conditions can shape the evolution of life in extraordinary ways. To understand the biology and life of prehistoric insects, scientists harness a combination of cutting-edge technologies and traditional methods. One of the most important historical sources of information comes from amber. This fossilized tree resin often traps insects, preserving them in remarkable detail. When researchers carefully excavate and examine these inclusions, they can study the morphology or structure of the insects, revealing vital clues about their appearance, size, and even behavior. In addition to visual analysis, advancements in imaging techniques, such as X-ray computed tomography, allow scientists to view the internal structures of these encased insects without damaging the fossils. This non-invasive method enables detailed studies of anatomical features, which can shed light on how these ancient creatures lived and interacted with their environment. By analyzing these features, researchers can piece together evolutionary lineages, allowing us to understand how today's insects may have adapted over millions of years. Moreover, the application of molecular biology techniques has further enhanced our comprehension of prehistoric insects. Scientists can extract genetic material from well-preserved specimens and analyze it to uncover their relationships with modern relatives. This aspect of research offers insights into the genetics of ancient species and helps to reconstruct the evolutionary tree of life, providing a narrative of how various traits may have developed over time. Finally, by studying the ecosystems in which these insects thrived, particularly through sediment analysis and the examination of plant fossils, scientists can better understand the environmental conditions of prehistoric times. Together, these methods form a comprehensive toolkit that helps illuminate the lives of insects from ages past, revealing the incredible diversity and complexity of life that existed long before humans arrived on Earth. During the prehistoric era, particularly in the Mesozoic and Paleozoic eras, the Earth experienced climatic conditions that were remarkably conducive to the flourishing of insect populations. The planet was much warmer than today, with fewer polar ice caps, which meant more terrestrial habitats were available for these creatures to inhabit. This warmth would have fostered longer growing seasons, allowing vegetation to thrive and provide ample food sources for various insect species. A significant aspect of prehistoric climates was the high concentration of atmospheric carbon dioxide. This elevated level not only supported lush plant growth, but also led to larger tree sizes and more extensive forests. These environments were not only rich in food, but also offered numerous niches for insects to explore and adapt. The vast diversity of plant life meant that insects could specialize and evolve, taking on roles as pollinators, scavengers, and predators within their ecosystems. Additionally, prehistoric Earth had periods of high humidity, particularly in tropical regions. These humid conditions granted insects access to essential resources like water and encouraged the formation of diverse habitats. Forests, swamps, and wetlands provided a multitude of environments where insects could thrive and diversify, leading to the emergence of many modern insect groups. This abundance of vegetation and moisture contributed to the high biodiversity we associate with prehistoric ecosystems. The lack of significant competition from other land animals during early periods also favored insect development. With fewer large herbivores and predators, insects could occupy a variety of ecological roles without the pressures that might limit their populations. By the time dinosaurs roamed the Earth, massive insects, some measuring up to several feet across, took advantage of these thriving conditions, demonstrating just how successful and diverse insect life became in those warm, lush, prehistoric environments. The extraordinary size of prehistoric insects, such as dragonflies with wingspans reaching nearly 2.5 feet, can be largely attributed to the higher levels of oxygen in the atmosphere during the Carboniferous period, around 300 million years ago. During this era, oxygen concentrations soared to about 35%, significantly richer than the 21% we breathe today. This abundance of oxygen allowed insects to grow larger than their modern relatives, as their respiratory system relied on passive diffusion to absorb oxygen. Insects breathe through a network of tiny tubes called tracheae that deliver oxygen directly to their tissues. Unlike mammals, these organisms lack lungs, meaning their size is limited by how effectively they can extract oxygen from their environment. The increased levels of atmospheric oxygen created a conducive environment for larger body sizes, as it meant that oxygen could diffuse more readily through their bodies. As a result, insects were able to develop and thrive at sizes that would be impossible in today's lower oxygen atmosphere. Additionally, the climate and ecology of the Carboniferous period provided an ideal habitat for these giant insects. The dense forests and humid conditions contributed to high moisture levels, which further supported their existence. With ample vegetation to feed on and fewer predators, insects flourished and explored various evolutionary paths, including growing to impressive sizes. The culmination of these factors highlights a fascinating interplay between atmospheric conditions and evolutionary adaptations. The rise in oxygen not only shaped the physical attributes of these creatures, but also impacted their life cycles and ecological roles, demonstrating how Earth's changing environments can ignite remarkable transformations in the natural world. The legacy of these giant insects reminds us of the incredible possibilities that have existed on our planet long before humans treaded upon it. During the prehistoric ages, giant insects flourished in a world far different from our own. One of the most significant geological events that influenced their habitats was the formation of supercontinents, particularly during the Carboniferous period, around 300 million years ago. This era was characterized by lush forests and vast swamplands, providing an abundant source of food and ideal conditions for insects to thrive and grow to enormous sizes. With the atmospheric oxygen levels at about 35%, significantly higher than today, insects evolved larger bodies, as their respiratory systems depended heavily on diffusion of oxygen. Additionally, the changing climates and tectonic activity over millions of years played pivotal roles in shaping insect habitats. As continents shifted, they altered ecosystems. Mountains rose and eroded, altering rainfall patterns and creating new habitats. For example, the uplifting of mountain ranges could lead to the formation of rain shadows, which created dry areas that had new ecological niches for insects to exploit. Such shifts encouraged diversity in habitats, favoring the evolution and adaptation of various insect species. The end of the Permian period, just over 250 million years ago, introduced one of the most drastic geological events, the largest mass extinction in Earth's history. This dramatic loss of flora and fauna, driven by volcanic eruptions and changing climates, deeply affected insect populations. Although it resulted in significant reduction in insect diversity, the survivors adapted to the new conditions, setting the stage for the evolution of different forms of life. As Earth's climate continued to fluctuate, it remained integral to the habitats of giant insects. The shifting of ocean currents and the cycles of glaciation and interglacial periods influenced the distribution of ecosystems, thereby affecting where these large creatures could live. Ultimately, the interplay of these geological processes and events created a dynamic environment, allowing enormous insects not only to arise, but to thrive in ways that would define their existence for millions of years. During the prehistoric era, known as the Paleozoic, particularly in the Carboniferous and Permian periods, giant insects emerged as some of the most fascinating denizens of the Earth. One of the most notable groups was the dragonflies, specifically a species known as Meganeura. These magnificent creatures had wingspans that could reach up to 2.5 feet, making them among the largest flying insects ever to have appeared. Their impressive size is attributed to the high oxygen levels of the atmosphere during that time, which allowed these insects to thrive and grow larger than their modern relatives. Another remarkable group of giant insects included the ancient orthopterans, which are the ancestors of modern grasshoppers and crickets. One famous representative was a creature named Arthropleura, a massive millipede-like arthropod that could grow up to 8 feet long. Despite resembling a modern-day millipede, Arthropleura was not an insect, but rather a myriapod. Its size instilled awe and demonstrates how conditions during the Carboniferous period were conducive to fostering large body sizes among various species. A black hole is an incredibly dense region in space where the gravitational pull is so strong that nothing, not even light, can escape from it. To understand how this cosmic phenomenon forms, let's look at the life cycle of a star. Stars begin their lives as huge clouds of gas and dust, primarily hydrogen. Through a process called gravitational collapse, this material comes together, forming a dense core. As the core compresses, it heats up and eventually ignites nuclear fusion, allowing the star to shine brightly for millions or even billions of years. Over time, a star uses up the hydrogen fuel in its core and begins to fuse heavier elements. When a massive star approaches the end of its life, it undergoes dramatic changes. It can expand into a red giant, shedding its outer layers and leaving behind a hot, dense core. If this core is large enough, it won't just become a regular remnant like a white dwarf or neutron star. Instead, it will collapse under its own gravity. This core collapse continues until it reaches a point of infinite density, creating a singularity. Surrounding this singularity is an invisible boundary known as the event horizon. Once any matter or radiation crosses this boundary, there's no turning back. It's drawn into the black hole. The process is driven by the immense gravitational forces at play, which can warp space and time itself. So, a black hole isn't just a space disaster. It's an extraordinary result of stellar evolution, showcasing the dynamic life and death of stars in our universe. Black holes themselves do not emit light, which makes them invisible to the naked eye and traditional telescopes. However, scientists have found clever ways to observe their presence and influence on nearby matter. One of the most significant methods involves studying the behavior of stars and gas that are close to a black hole. When a star orbits a black hole, it can be seen moving in a rapid and unpredictable manner. By tracking these movements, scientists can infer the mass of the black hole exerting its gravitational pull. Another fascinating method comes from the material surrounding a black hole, often referred to as an accretion disk. This disk forms from gas and dust that spirals inwards. As this matter gets closer to the black hole, it accelerates and heats up to extremely high temperatures, emitting powerful radiation, especially in the form of X-rays. Observing this radiation allows scientists to detect the black hole indirectly. In recent years, advanced technology has enabled even more groundbreaking developments. The Event Horizon Telescope, a network of linked radio dishes around the world, was able to capture an image of the shadow of a black hole. This shadow is the outline of the black hole against the glowing gas of the accretion disk, providing direct evidence of its existence. Thus, by studying how objects behave in the vicinity of black holes and by detecting high-energy emissions from surrounding material, scientists have been able to gather substantial evidence of these mysterious cosmic phenomena, piecing together the puzzle of their existence despite their inherently invisible nature. The event horizon of a black hole is a boundary in space that holds great significance. Imagine it as an unseen line marking the point of no return. When anything crosses this threshold, it cannot escape, not even light. This is why black holes appear black. They trap everything that ventures too close. Understanding the event horizon helps us grasp the strange nature of black holes. It signifies where gravitational pull becomes so intense that space and time begin to behave unusually. Inside the event horizon, the rules of physics as we know them start to break down. Time can stretch and slow down, creating bizarre effects for observers at a distance. Scientists use the event horizon to study the mechanics of black holes, including how they grow and interact with their surroundings. Observing the light or energy emitted by material as it approaches this boundary gives valuable insights into the black hole's size, rotation, and the laws of physics under extreme conditions. The event horizon is a gateway into understanding some of the most puzzling elements of our universe, challenging our perceptions of reality and the fabric of space-time itself. Measuring the mass of a black hole might seem like a daunting task, but scientists have developed clever methods to do just that. Since black holes do not emit light, they cannot be measured directly. Instead, scientists look at the effects they have on their surroundings. One common approach involves observing the motion of stars or gas clouds near a black hole. Just like how you can judge how heavy a person is by the way they push against the ground when they move, the way objects move around a black hole can give clues about its mass. If a star is orbiting around an invisible object and moving quickly, it indicates that the object, in this case, the black hole, is very massive. Using the principles of gravity, scientists apply a fundamental rule. The strength of gravity from an object determines how fast other objects will move in its vicinity. By measuring the speed of the orbiting stars and the distance from the black hole, scientists can work out how much mass the black hole must have to exert that gravity. In addition, another technique involves examining the light emitted by hot gas as it spirals into a black hole. As this gas accelerates and heats up, it emits X-rays, high-energy light that can be detected by instruments. The behavior of this gas, how fast it moves, and how it interacts with the black hole can also provide valuable information about the black hole's mass. Finally, scientists can even study gravitational waves, ripples in space-time caused by massive objects colliding, such as two black holes merging. The way these waves spread out through space carries information about the masses of the black holes involved. By piecing together these observations and measurements, scientists can build a clearer picture and get a precise estimate of a black hole's mass, transforming mystery into knowledge about these extraordinary cosmic phenomena. Black holes are fascinating cosmic phenomena that come in several distinct types, each with its own unique characteristics. The most common classification divides them into three main categories: stellar black holes, supermassive black holes, and intermediate black holes. Stellar black holes form when massive stars exhaust their nuclear fuel and undergo a catastrophic collapse at the end of their life cycle. This collapse compresses the star's core, creating a region where gravity is so intense that not even light can escape. These black holes typically have masses greater than a few times that of our Sun, and they can often be detected by the light emitted when they pull in nearby gas and debris. Supermassive black holes are dramatically different. These giants can possess the mass equivalent to millions or even billions of suns. They reside at the centers of most galaxies, including our Milky Way. The origin of supermassive black holes is still a mystery, but they likely formed from the merging of smaller black holes and the accretion of vast amounts of gas and dust over billions of years. Their influence is so powerful that they help shape the structure of their host galaxies. Intermediate black holes represent a less common, though equally intriguing category. They have masses that fall between those of stellar and supermassive black holes. While their existence was once largely theoretical, recent observations suggest they may form from the merger of multiple stellar black holes in dense star clusters. These intermediate black holes could play a crucial role in understanding the evolution of galaxies. Additionally, there are theoretical black holes, such as primordial black holes, which could have formed shortly after the Big Bang. These black holes are thought to be very small and could vary widely in mass. However, their existence remains speculative, and more evidence is needed to confirm their presence. Each type of black hole provides insight into the mysteries of the universe, offering clues about star formation, galaxy evolution, and the fundamental laws of physics. As scientists continue to explore these cosmic giants, our understanding of the universe keeps expanding. A black hole profoundly influences both time and space in its vicinity. To understand this, imagine space as a stretched-out rubber sheet. When a heavy object, like a black hole, is placed on it, the sheet curves down significantly around that object. This curvature represents how gravity works. The greater the mass of an object, the more it distorts space around it. When it comes to time, the effects are just as dramatic. Think of time as a flowing river. Near a black hole, the river slows down considerably. If an observer were to watch someone close to a black hole, they would see that person's actions occur much more slowly compared to their own experience of time, which remains normal. This phenomenon is called time dilation, and it occurs because the intense gravity of the black hole warps both space and time, creating a curious relationship where they cannot be treated separately. As one nears the black hole, particularly at its boundary known as the event horizon, the effects become even more extreme. From the perspective of outsiders, someone falling into the black hole appears to move slower and eventually freeze at the edge, fading away slowly as light struggles to escape. However, for the person crossing into the black hole, they would not feel any difference initially. Instead, they plunge into a region where the rules of physics as we understand them begin to break down. The interplay of time and space around a black hole paints a fascinating picture of the universe's mysterious and extreme nature. The mystery of what lies beyond a black hole is one of the most intriguing questions in astrophysics. Traditionally, when we think about black holes, we imagine an impenetrable barrier beyond which nothing can escape, not even light. This leads to a region known as the event horizon, which acts as the point of no return. But what happens inside the black hole, or beyond its edge, remains a subject of great speculation and debate. One current theory is that beyond the event horizon, matter is crushed into an infinitely small point called a singularity. At this point, the laws of physics as we understand them cease to function normally. Time and space become incredibly warped, and our usual understanding of the universe does not apply. This suggests that the environment inside a black hole is vastly different from the one we experience. Another fascinating idea is the possibility of wormholes. Some scientists propose that black holes could connect to other regions of the universe, or even to other universes entirely, creating a bridge-like structure. This means that traveling through a black hole might not lead to oblivion, but could potentially open a doorway to an entirely different area of space and time. Additionally, there is a concept known as the information paradox, which challenges our understanding of what happens to information that falls into a black hole. According to quantum mechanics, information cannot be destroyed, yet if something disappears beyond the event horizon, it seems lost forever. Researchers are investigating whether the information might be preserved in some form at the event horizon, hinting that there may be a deeper layer of reality that we have yet to comprehend. Lastly, some theories suggest that black holes might be gates to parallel universes or alternate dimensions. This would fundamentally change our understanding of the cosmos, implying that the universe is much more interconnected than we currently perceive. Each of these theories opens up exciting possibilities and leads to new questions about the nature of reality, pushing the boundaries of science and our understanding of the universe we inhabit. Exoplanets are planets that exist outside our solar system, orbiting stars other than our Sun. Imagine the vast universe filled with countless stars, and each of those stars could potentially host its own planets. Exoplanets vary widely in size, composition, and distance from their host stars, giving scientists a rich field of study to explore. The discovery of exoplanets is an exciting and innovative process. While early observations relied on detecting changes in starlight, modern methods have become more sophisticated. One prominent technique involves monitoring stars for a slight dimming effect. When a planet crosses in front of a star from our perspective, it blocks a tiny amount of light, causing a brief decrease in brightness. This method is known as the transit method and has led to many confirmed discoveries. Another technique is radial velocity, which looks for the wobble of a star caused by the gravitational pull of orbiting planets. As a planet revolves around a star, its gravity pulls the star slightly, causing it to move in a small circle. This movement creates detectable changes in the star's light spectrum, revealing the presence of a planet. As technology advances, new methods continue to emerge, like direct imaging, where astronomers capture pictures of exoplanets by blocking out their star's light. Each of these methods expands our understanding of the universe, revealing a wealth of planetary systems, some potentially similar to our own. Exoplanets challenge our ideas about the formation of planetary systems and the possibilities for life beyond Earth. Determining the habitability of an exoplanet, which is a planet outside our solar system, involves a careful analysis of various factors. Scientists start by looking for planets located in what is known as the habitable zone around a star. This zone is the region where conditions might be just right for liquid water to exist, essentially the Goldilocks zone, where it's not too hot and not too cold. This fascinating interplay of biology and environment demonstrates how these mighty creatures navigated a world filled with both threats and opportunities, ultimately shaping the evolution of life as we know it today. Insects, often seen as mere pests, play a pivotal role in the evolutionary story of many predators. The sheer diversity and abundance of insect species create a rich tapestry of interactions within ecosystems. Predators, such as birds, reptiles, and mammals, have had to adapt to these changing environments, often refining their hunting skills, physical characteristics, and even their social behaviors in response to the availability and behavior of insects. For instance, consider the evolution of bird species that primarily feed on insects. These birds often develop specialized beaks suited for extracting insects from narrow crevices or grasping them in mid-air. Over time, their eyesight may enhance, enabling them to spot even the slightest movements in the underbrush, increasing their chances of a successful hunt. This adaptation is a direct response to both the abundance and the evasive tactics of their insect prey, underscoring a fascinating arms race between predator and prey. Furthermore, the presence of insects influences the reproductive strategies of their predators. In some cases, predators may exhibit variations in breeding times or clutch sizes depending on food availability. During seasons when insects thrive, a predator might produce more offspring, a strategy that boosts their chances of survival in a competitive world. This relationship shows us that evolution is not just a linear progression. It's a complex interplay of various life forms adjusting to each other's presence. Lastly, insects also carry diseases and parasites, which have forced predators to develop resistance. Some species may evolve immunity to these threats, creating a cycle of adaptation that can lead to increased biodiversity. This dynamic emphasizes the interconnectedness of life on Earth, illustrating how the presence of insects has not only shaped their own lineage, but has propelled a broader evolutionary change in countless species of predators. Through these fascinating interactions, we see the intricate web of life unfold, revealing the beauty of evolution as a continual process forged by relationships and responses within ecosystems. In the ancient ecosystems where giant insects roamed nearly 300 million years ago, their interactions with plants and animals were pivotal in shaping the environment. During this period, known as the Carboniferous era, oxygen levels were significantly higher than today, exceeding 30%. This surplus allowed insects to grow larger, fueling their predatory and competitive behaviors within their habitats. Giant insects, such as dragonflies with wingspans reaching 2.5 feet, were at the top of the food chain. They hunted smaller insects and even other small animals, showcasing their impressive size and agility. Their presence influenced the evolution of other species, driving smaller insects to develop various adaptations for evasion and survival. This led to a unique dance of predator and prey, where each played a crucial role in maintaining ecological balance. In terms of their interaction with plants, giant insects also contributed significantly to pollination processes. During a time when flowering plants were just beginning to evolve, these insects would transfer pollen from one blossom to another, promoting genetic diversity. This symbiotic relationship benefited both parties. Plants flourished and spread, while insects took advantage of the abundant food sources found in flowers and foliage. As these massive insects thrived, they also left behind a legacy of organic material. Their waste products added vital nutrients back into the soil, promoting robust plant growth. The intricate relationships between giant insects, plants, and other animals highlight the complexity of ancient ecosystems, revealing a fascinating picture of life on Earth long before mammals took center stage. During prehistoric times, giant insects played a crucial role in the ecological balance of their environments, serving as both predators and prey in the food chain. Evidence suggests that during the Carboniferous period, approximately 300 million years ago, insects were much larger than today. Some could reach lengths of up to 2 feet, largely due to the higher levels of oxygen in the atmosphere. This increased oxygen allowed insects to grow larger and thrive, affecting the dynamics of the ecosystems they inhabited. These colossal insects were significant predators in their surroundings, often feeding on smaller insects and various plant life. For instance, the dragonfly-like Meganeura, with a wingspan the size of a crow, would have been a fearsome aerial predator. These giant insects helped control populations of smaller species, contributing to the overall health of the environment. Their place in the food chain was pivotal, as they not only kept the numbers of other organisms in check, but also interacted closely with plant life, playing a role in pollination and seed dispersal. At the same time, giant insects themselves were prey for larger animals that would eventually emerge, including early reptiles and amphibians. This intricate web of relationships illustrates how these massive creatures contributed to feeding the next tier of the food chain, promoting biodiversity and the evolutionary arms race that characterized these ancient periods. As predators and prey, they were essential players in shaping the ecosystems of their time. The decline of giant insects wasn't a sudden event, but rather part of a larger evolutionary process over millions of years, influenced by climate change and the rise of larger vertebrates. Though they eventually became extinct, their role in prehistoric food chains highlights a fascinating chapter in the story of life on Earth, revealing how interconnected and dynamic prehistoric ecosystems truly were. Their legacy reminds us of how changes in environmental conditions can drastically affect the scale and structure of life in any given era. Giant insects once roamed the Earth during the Carboniferous period, roughly 300 million years ago. This era saw the rise of remarkable creatures, with some insects reaching sizes that seem almost mythical today. For instance, the dragonfly-like Meganeura had a wingspan of over 2 feet, while the giant cockroach, which could grow nearly a foot long, scuttled across the ancient landscapes. The sheer size of these insects significantly changed the dynamics between various species within their environments. With their enormous sizes, these insects occupied ecological niches that many modern creatures could not. They served as both predators and prey, influencing the populations of smaller animals and plants. As predators, giant insects hunted other organisms, which helped control pest populations. This predatory behavior ensured healthier ecosystems by maintaining a balance between various species. Additionally, their unique feeding strategies also played a role in how vegetation thrived or struggled in their habitats. Moreover, the sheer biomass created by these giant insects contributed significantly to the decomposition processes of the time. As they fed on decaying plant matter, they would help recycle nutrients back into the soil, enriching the Earth's surface and promoting plant growth. Their presence, therefore, revolved around a complex interaction where they not only recovered energy from their environment, but also supported the habitats in which they lived. However, the decline of these giant insects, likely influenced by evolving climatic conditions and competition from emerging vertebrates, marked a significant shift in ecological balance. With their disappearance, ecosystems began to stabilize around smaller insects, which adapted to the changing environments. The ancient world, once dominated by giants, eventually transitioned to the more familiar landscapes we recognize today, with a newfound balance that continues to evolve. In the annals of paleontology, few discoveries capture the imagination quite like the giant insects that once roamed the Earth. One of the most notable findings comes from the Carboniferous period, around 300 million years ago, when some of the largest insects on record were alive. Fossils of creatures like the Meganeura, a dragonfly-like insect with a wingspan of approximately 2 feet, reveal a world where giant insects thrived in lush, swampy environments rich with vegetation. With ventral spiracles that allowed them to breathe in the oxygen-rich atmosphere of that time, these remarkable insects soared through ancient skies. Another significant fossil discovery is that of the Titanoptera, a colossal grasshopper-like insect that lived during the Permian period around 265 million years ago. Fossils suggest that Titanoptera could have reached lengths of up to 8 inches, making it one of the largest known terrestrial insects. These creatures not only astonish scientists with their size, but also provide insights into the ecological dynamics of their respective periods, revealing how climate and atmospheric conditions influenced insect evolution. The discovery of these insects often occurs in places rich in sedimentary layers, such as coal mines or shale deposits, where conditions favored the preservation of such delicate structures. Insects, due to their exoskeletons, can fossilize exceptionally well under the right conditions, allowing scientists to study their morphology and gain a deeper understanding of ancient ecosystems. These fossil records have even helped reconstruct the atmospheric conditions of the time, leading researchers to conclude that higher levels of oxygen may have contributed to the gigantic sizes of these insects. In more recent discoveries, researchers have also found fossils that showcase a variety of other intriguing characteristics, such as elaborate wings and unique adaptations that point to how these insects interacted with their environments. Through examining the remains of these astonishing creatures, scientists continue to piece together the complex puzzle of Earth's biological history, reminding us that our planet once hosted a vastly different array of life forms, some far beyond our current imagination. Fossils are like windows into our planet's distant past, offering vital clues about prehistoric ecosystems and the life forms that inhabited them. Each fossil tells a unique story, providing insights into how ancient species interacted with each other and their environments. By studying these remnants, scientists can reconstruct the complex web of life that existed millions of years ago, revealing not only what organisms lived, but also how they thrived, adapted, and eventually evolved. For instance, the discovery of plant fossils alongside animal remains helps paleontologists piece together the food webs of ancient environments. Fossils of herbivorous creatures indicate the types of vegetation that once flourished, while the presence of carnivorous predators tells us who was hunting whom and what the ecosystem looked like as a whole. This interconnectedness offers a glimpse into how climate and geography shaped the biosphere over time, influencing species diversity and distribution. Moreover, fossils can highlight significant events in Earth's history, like mass extinctions and climatic shifts. By analyzing fossilized remains from different geological periods, researchers can track changes in biodiversity over time, understanding how ecosystems responded to environmental pressures. Such analyses reveal patterns of resilience and vulnerability among species, shedding light on how life has persisted through dramatic shifts. The study of fossils enriches our knowledge of ancient biomes, presenting a detailed picture of life on Earth long before human existence. From lush forests to sprawling deserts, every fossilized trace contributes to a narrative that not only fascinates but also underscores the delicate balance of life that continues to evolve and transform. Across the globe, noteworthy discoveries of giant insect fossils have sparked the curiosity of both scientists and enthusiasts. Notably, the Green River Formation in present-day Wyoming, Utah, and Colorado is famous for its well-preserved fossils from the Eocene epoch. This region offers a rich trove of ancient life, with insect fossils showing impressive sizes that might astonish us today. For instance, dragonfly fossils uncovered here have wingspans reaching more than 2 feet, suggesting the atmospheric conditions of that time supported larger insects. In addition to North America, the cliffs of France have also yielded remarkable finds. The sedimentary rocks in this region have revealed fossilized insects, including large species of mayflies and other remarkable arthropods that hint at the diversity of prehistoric ecosystems. The quality of preservation is ample, providing insights into both the structure and lifestyle of these ancient creatures. Further afield, tropical amber deposits across various parts of the world, especially in the Dominican Republic and Myanmar, have become an astonishing source of insect fossils. These fossilized insects, often trapped in tree sap millions of years old, sometimes reveal larger varieties that existed long before our time. Not only do they showcase the fascinating spectrum of insect evolution, but they also help researchers piece together ancient climates and environments. Even in 2023, new excavation sites continue to be explored, fueling our excitement and understanding of the history of life on Earth. The story of giant insects is not just about size. It reflects the intricate balance of ecosystems and how they have evolved over millions of years. Every new find reminds us of a planet filled with diverse and dramatic histories waiting to be unraveled. Paleontologists employ a variety of methods to study fossilized giant insects, illuminating insights about these fascinating creatures and their environments. One of the primary techniques involves examining the physical characteristics of the fossils, often discovered in sedimentary rock layers or amber. By carefully analyzing the size, shape, and structural details of the fossils, scientists can glean significant information regarding the ancient biology and behavior of these insects. Another essential method is the use of imaging technology. Techniques such as scanning electron microscopy allow researchers to observe surface details that are invisible to the naked eye. This not only aids in identifying specific types of insects, but also reveals delicate structures, such as the fine hairs on a body or intricate wing patterns. In combination with three-dimensional imaging, these techniques create a clearer picture of how these insects once lived and interacted with their environment. Paleontologists also utilize chemical analysis to understand the environmental conditions during the time these insects thrived. This might involve studying the isotopic composition of materials surrounding the fossils, which can provide insights into temperature and atmospheric conditions. Further, the analysis of amber inclusions, where some of these insects are often found preserved, helps paint a picture of the flora and fauna that coexisted with them, creating a narrative of the ecosystems from millions of years ago. Lastly, comparisons with modern insect relatives play a crucial role in the study of fossilized giant insects. By examining the evolutionary relationships between these ancient organisms and contemporary species, paleontologists can infer behavioral patterns, habitat preferences, and adaptations to changing environments. By pulling together these diverse methods, scientists continuously deepen our understanding of these remarkable prehistoric creatures and their role in the history of life on Earth. Researchers utilize a fascinating combination of techniques to reconstruct the behaviors and appearances of extinct giant insects. This scientific endeavor starts with the study of fossilized specimens. Paleontologists analyze these fossils to glean information about the physical structure of these insects, including their size, shape, and any distinctive features. These fossils often contain crucial details about wing structures, leg configurations, and the types of adaptations these insects had for their environments. Additionally, the examination of fossilized tracks and burrows provides insight into how these creatures moved and interacted with their surroundings. By studying these imprints, scientists can infer behaviors such as walking patterns, predation, and even social interactions. The meticulous work of analyzing these traces allows researchers to piece together a more dynamic picture of life as it was millions of years ago. Modern technology plays a crucial role in this reconstruction. Advanced imaging techniques, like CT scans, enable scientists to create three-dimensional models of insect fossils, revealing internal structures that were once hidden. Furthermore, comparative studies with living relatives of these extinct giants help researchers understand potential behaviors. For instance, studying the habits of current-day beetles or dragonflies can provide clues about how their ancient counterparts might have lived. By integrating data from multiple sources, including fossil analysis, ecological modeling, and comparisons with living species, researchers create a holistic picture of these extinct insects. This multifaceted approach not only brings their appearances to life, but also paints a vivid picture of their environment and ecosystems, allowing us to appreciate the incredible diversity that once thrived on Earth. Technology plays an essential role in the analysis and interpretation of ancient creatures, unlocking secrets locked in the fossil record. From the early days of paleontology, simple tools like chisels and brushes helped scientists uncover fossils buried in rock. Now, we have advanced technologies that take our understanding of these ancient beings to a whole new level. One significant breakthrough comes from three-dimensional imaging techniques, such as computed tomography. This allows researchers to create detailed scans of fossils without damaging them. By slicing through the rock virtually, scientists can examine the interior structures of these specimens, offering insights into their anatomy and evolutionary history. This non-invasive approach can lead to discoveries that traditional methods might miss, revealing previously unseen features of these ancient creatures. Moreover, technology like scanning electron microscopes enables researchers to study fossils at an incredibly small scale. This method reveals the delicate structures on the surface of bones or shells, providing insights into how these creatures may have interacted with their environment. For example, scientists can analyze bite marks on fossils, helping them infer the feeding habits of long-extinct species. Additionally, advances in genetic analysis play a crucial role in interpreting the evolutionary relationships between ancient creatures. By extracting and sequencing ancient DNA, researchers can unveil the genetic blueprints of species that lived millions of years ago. This genetic information helps elucidate how these creatures adapted to their environments, transforming our understanding of life on Earth's ancient landscapes. Technology serves as a time machine, guiding us through the complexities of ancient life and reshaping our comprehension of evolution itself. Insects are among the most diverse creatures on our planet, and an exploration of their size and diversity reveals fascinating insights into their evolution. Today, there are over 1 million described species of insects, and some estimates suggest that as many as 10 million total species may exist. This astonishing variety is a hallmark of modern insects, but pales in comparison to the colossal forms that roamed the Earth hundreds of millions of years ago. During the Carboniferous period, approximately 300 million years ago, some insects reached extraordinary sizes. For instance, dragonflies had wingspans of nearly 2.5 feet, a size made possible by the higher oxygen levels in the atmosphere at that time. The large size of these prehistoric insects illustrates how environmental conditions can drastically shape life forms. Similarly, ancient cockroaches and other species grew much larger than their modern relatives, showcasing evolutionary adaptations that rarely occur today. While modern insects may not boast the same intimidating sizes as their prehistoric ancestors, they excel in diversity and specialization. Today's insects inhabit virtually every corner of the Earth, adapting to various environments, from the deepest jungles to arid deserts. This adaptability has given rise to intricate relationships with plants, animals, and even humans. For example, pollinators like bees and butterflies play crucial roles in ecosystems and agriculture, underscoring how critical modern insects are to our world. Despite the absence of giant insects, the variety of shapes, colors, and behaviors we see today speaks volumes about the evolutionary journey of these creatures. Each species, whether it's a tiny ant or a strikingly colored butterfly, contributes to a complex web of life. This ongoing saga of evolution shows that while some prehistoric giants may be gone, the innovation and adaptability of insects continue to thrive, revealing the remarkable resilience of life on Earth. Throughout history, the phenomenon of gigantism has fascinated scientists and laid the groundwork for many intriguing studies. Today, we continue to witness remarkable examples of large insects that challenge our typical perceptions of size. One prominent example is the Goliath beetle, known to measure up to 15 centimeters in length. Native to the rainforests of Africa, these majestic creatures are not just impressive in size, but they also display striking patterns and colors that highlight their unique beauty. Another notable instance of insect gigantism can be observed in the Titanus giganteus, commonly known as the Titan beetle. Originating from the Amazon rainforest, this extraordinary insect can reach lengths of up to 20 centimeters and is considered one of the largest beetles in the world. Its sheer size, coupled with powerful mandibles, makes it a fascinating subject for entomologists and a stunning example of adaptations to its environment. Furthermore, we must consider the giant weta, a type of cricket native to New Zealand. Some species of these flightless insects can weigh over 70 grams, making them heavier than many small mammals. The giant weta thrives because of New Zealand's unique ecosystems, where it has evolved without the pressures of certain predators found in other parts of the world, allowing it to grow to such remarkable sizes. Insects like these challenge our understanding of biological constraints and ecological niches. They not only exemplify the wonders of evolution and adaptation, but also shed light on the delicate balance between size and the demands of the environment. As we study these magnificent creatures, we gain insight into the fascinating world of insect life and the conditions that can lead to extraordinary sizes. Insects, with their remarkable diversity, have a fascinating evolutionary story that stretches back more than 400 million years. The earliest ancestors of modern insects were simple, aquatic creatures that gradually transitioned to land during a significant period known as the Devonian era. As they colonized terrestrial environments, these primitive insects developed key adaptations, including the ability to breathe air through specialized structures and protective exoskeletons that allowed them to survive in varying conditions. Over time, insects underwent significant evolutionary changes, leading to the emergence of new forms and functions. For instance, the development of flight was a monumental turning point in insect evolution. Winged insects first appeared around 300 million years ago. This adaptation not only allowed them to escape predators, but also opened up new ecological niches, enabling them to reach diverse environments, from lush forests to arid deserts. The transition to true flight was made possible by intricate skeletal structures, specialized muscles, and a unique method of developing wings. The evolutionary pressure of natural selection also played a critical role in shaping modern insects. As they interacted with other organisms like plants and predators, they adapted in ways that enhanced their survival. This led to the evolution of many unique traits, such as the ability to camouflage, complex mating rituals, and even social structures seen in species like bees and ants. These adaptations increased their resilience and allowed insects to thrive in nearly every habitat on Earth. Today, insects are the most successful group of animals in terms of species richness and ecological roles. They contribute significantly to ecosystems as pollinators, decomposers, and even as sources of food for other wildlife. The intricate relationships they have formed over millions of years with plants and other animals underlines their importance in maintaining biodiversity and healthy ecosystems. This evolutionary journey from simple aquatic life to the highly specialized insects we see today demonstrates not only the adaptability of life, but also the fascinating complexities of evolutionary processes. Throughout Earth's history, there have been several significant extinction events that contributed to the decline of giant insects. During the Carboniferous period, which lasted from about 300 million to 360 million years ago, insects thrived and grew to impressive sizes. This era was characterized by high oxygen levels in the atmosphere, which allowed insects to evolve larger body sizes. Fossils from this time showcase fascinating specimens like dragonflies with wingspans of nearly 2 feet. However, as the planet transitioned into the Permian period, significant environmental changes began to unfold. The atmosphere experienced reductions in oxygen levels and dramatic shifts in climate. The Permian Triassic extinction event, roughly 252 million years ago, is particularly noteworthy. It is considered the most severe extinction event in Earth's history, wiping out approximately 95% of all marine species and around 70% of terrestrial vertebrates. These drastic changes undoubtedly affected the ecosystems that supported giant insects, leading to their gradual decline. The evolution of dinosaurs in the Mesozoic era also played a role in the fate of these large insects. As these reptiles grew in size and numbers, they altered ecosystems and ecological dynamics. Insects, now contending with new predators and competitors, found it increasingly challenging to maintain the sizes they once sported. By the end of the Cretaceous period, with the catastrophic asteroid impact that led to another mass extinction around 66 million years ago, many insects had adapted to a more modest size, better suited for their new world where smaller forms often fared better in surviving rapid changes. Today, while insects remain vital components of ecosystems, they have generally retained smaller dimensions. The reasons behind these changes are multifaceted, influenced heavily by the long evolutionary journey of life on Earth, a story marked by triumphs, catastrophes, and adaptation. Understanding the past enables us to appreciate the delicate balance of life today and the myriad factors that shape the organisms we see around us. The disappearance of many ancient creatures, particularly during major extinction events, can be closely tied to significant changes in Earth's environment. These transformations often disrupt the delicate balance of ecosystems, resulting in the rapid decline of species unable to adapt. One of the most impactful factors has been climate change, which can lead to shifts in habitat, food availability, and water sources. For instance, during the Permian-Triassic extinction event, around 250 million years ago, Earth experienced dramatic temperature fluctuations and a decrease in oxygen levels. Such extreme conditions created inhospitable environments for many species, leading to a staggering loss of biodiversity. About 90% of marine life and 70% of terrestrial vertebrates vanished. It was a time when the Earth's climate shifted from what was once stable, resulting in massive volcanic eruptions releasing greenhouse gases and altering ocean chemistry. Another critical factor influencing extinction was the change in sea levels. As glaciers expanded and contracted, regions that were once submerged became land, while other areas were flooded. These alterations affected shallow marine habitats, which are crucial for many species during their life cycles. Coastal creatures were particularly vulnerable, as the availability of breeding grounds and food sources fluctuated with the changing tides. Lastly, the encroachment of new species, whether through migration or ecological shifts, could put additional pressure on native populations. Competition for resources, predation, and disease introduction led to the decline of many once thriving species. Understanding how these environmental changes intertwined with biological factors gives us insight into the resilience of life on Earth and the ever-present challenges it faces. The extinction of a species can often be traced back to a complex interplay of biological factors, including competition within ecosystems and the impact of diseases. When two or more species vie for the same resources, be it food, shelter, or breeding grounds, the stronger competitor can decisively influence the survival of the others. This competitive dynamic can lead to shifts in population levels, with weaker species declining, often to the point of extinction, if they are unable to adapt to changing conditions. Moreover, diseases can play a critical role in wiping out populations. When a pathogen spreads through a species, it can decimate individuals who lack immunity. This is particularly concerning in isolated ecosystems where species have not encountered certain diseases before. The introduction of a new disease can therefore represent a deadly threat that certain species are ill-equipped to handle, leading to dramatic declines and potential extinction. However, competition and disease do not operate in isolation. There are often multiple factors at play. Habitat loss due to human development or environmental changes often exacerbates competition among species vying for limited resources. A dwindling habitat forces animals to come into closer contact than ever before, heightening the likelihood of disease transmission and increasing stress, which can suppress immune responses and make populations more vulnerable to illness. The extinction of various species can often be linked to the complexity of interactions within ecosystems. Competition for resources and the emergence of diseases significantly contribute to the decline of susceptible populations. These biological factors are compounded by environmental changes that disrupt habitats, ultimately leading to the tragic loss of biodiversity on our planet. Understanding these dynamics is crucial for conservation efforts aimed at protecting those species that still face existential threats. The discovery of giant insects has had a profound impact on popular culture and media, sparking a fascination that has transcended generations. When scientists began uncovering prehistoric remains of gigantic insect species, such as the dragonfly with a wingspan of nearly 2 feet, it ignited imaginations and provoked questions about evolution and the conditions of ancient Earth. These findings found their way into literature and film, inspiring tales that explore the extreme consequences of biological anomalies and the wonders of nature. One of the most significant influences can be traced back to early science fiction and horror films. Movies like Them from the 1950s showcased enormous ants, playing on both the fear of nature's unchecked power and the fascination with scientific experimentation. These films often tapped into the anxieties of the nuclear age, reflecting societal fears about technology and its potential to disrupt natural order. The concept of oversized insects became symbolic of chaos and human vulnerability in the face of nature's might. In literature, authors have long used giant insects as metaphors. Works like Franz Kafka's The Metamorphosis prompt readers to reflect on identity and transformation, while others, like H.G. Wells's stories, challenge the boundaries of human understanding and the consequences of meddling with nature. The stark imagery of oversized insects not only evokes awe, but also evokes moral and philosophical considerations regarding humanity's role in the ecosystem. Today, giant insects continue to resonate in video games, animation, and even merchandising, where they often capture both a sense of horror and a comic lightness. Shows like The Magic School Bus have made these topics educational, teaching young audiences about biology and ecosystems through engaging narratives. The continued evolution of giant insect representations in popular culture signals an ongoing curiosity about the natural world, reminding us that our fear and fascination with these creatures mirror our own complexities as a species navigating an ever-changing environment. Prehistoric creatures, often known as dinosaurs and other ancient life forms, have significantly shaped our understanding of evolution, biology, and Earth's history. Their existence, stretching over millions of years, provides vital clues about the processes that have shaped the planet's ecosystems. Scientists have dedicated themselves to unraveling the mysteries of these ancient beings by studying fossils, which tell us about their structure, behavior, and environments. This deep dive into paleontology not only reveals fascinating insights, but also inspires curiosity and exploration in various scientific fields. The size and diversity of these prehistoric creatures have sparked investigations into how life adapts to changing environments. Researchers are particularly interested in how species evolve over time in response to climate shifts, natural disasters, and competition for resources. By examining the fossil record, scientists can identify patterns of extinction and the subsequent rise of new species. This knowledge is crucial in understanding current biodiversity and the potential impacts of modern climate change, making the study of these ancient organisms incredibly relevant today. Innovations in technology have further fueled our exploration of prehistoric life. Advances in imaging techniques allow for more detailed analysis of fossils, including their internal structures, which helps scientists piece together how these animals lived and interacted with their surroundings. Additionally, molecular biology techniques have begun uncovering genetic information from ancient remains. With these tools, researchers can not only recreate the appearance of these creatures, but also explore their behavior and social structures, shedding light on what it was like to share the Earth with such remarkable beings. Moreover, the allure of prehistoric creatures extends beyond scientific inquiry. They have captured public imagination, leading to increased funding for research and education in paleontology. Exhibits at museums and popular culture, representations in films and literature spark enthusiasm and foster a deep appreciation for the Earth's ancient past. This fascination ensures that the study of prehistoric life continues to benefit our understanding of biology, ecology, and the very fabric of our planet's history, inspiring future generations of scientists and curious minds alike. Giant insects occupy a unique space in both documentaries and fiction, captivating audiences with their blend of fascination and fear. These oversized creatures tap into primal instincts, sparking our curiosity about the natural world and our place within it. Their exaggerated features and movements can evoke a sense of the uncanny, inviting viewers to reflect on the marvels of evolution, adaptation, and the often overlooked complexity of smaller life forms. In documentaries, giant insects are sometimes presented as a lens through which we can explore ecological themes. They serve as vivid examples of evolution in action, showcasing how certain species, like dragonflies or beetles, have fascinating adaptations that enable survival in diverse environments. Through stunning visuals and detailed explanations, these programs highlight the roles these creatures play in their ecosystems, from pollinators to predators, while also emphasizing the delicate balance of nature. Fiction takes this concept a step further by amplifying the characteristics of insects to an extraordinary level. Films and literature have depicted giant insects as both monstrous and magnificent, often personifying them to create relatable or terrifying antagonists. This exploration of size exaggerates their behaviors and capabilities, inviting a deeper contemplation about humanity's fear of the unknown and the environments we inhabit. It's this interplay of awe and anxiety that keeps audiences on the edge of their seats. Moreover, giant insects symbolize our fears of societal collapse and the unpredictable power of nature. They remind us that even the smallest creatures can possess immense strength, urging a reconsideration of the natural hierarchy we often associate with size. By weaving together the factual and the fictional, giant insects become more than mere monsters. They emerge as a symbol of the wonders and threats posed by the natural world, making them unforgettable figures in both documentaries and storytelling alike. Throughout Earth's history, there have been remarkable creatures that roamed the planet, many of which would seem extraordinary and perhaps terrifying to us today. Among them, giant insects stand out, particularly from the Paleozoic era, when conditions on Earth favored larger forms of life. One of the most iconic giant insects is the Meganeura, a prehistoric dragonfly that lived around 300 million years ago. With a wingspan extending up to 2.5 feet, Meganeura was not just a giant insect, but a masterful predator of its time, capable of catching smaller insects in mid-air. Its sheer size was likely supported by the higher levels of oxygen in the atmosphere back then, allowing insects to grow much larger than those we see today. Another striking example of giant insects is the Arthropleura, which, while technically a millipede rather than an insect, is often associated with this group. This creature measured over 8 feet long, making it one of the largest terrestrial invertebrates to ever exist. Arthropleura thrived during the Carboniferous period, a time when the Earth was largely covered by dense forests. The combination of thick vegetation and a warm climate resulted in a unique ecosystem that could support such colossal life forms. However, its size must have also made it vulnerable to predation, particularly from larger amphibians of that age. One of the most terrifying images conjured by giant insects is that of the Titanoboa. Although technically a snake, it represents the evolutionary path of massive creatures in a time when the Earth was teeming with large life. Living approximately 60 million years ago, Titanoboa was about 40 feet long, dwarfing the largest modern snakes. Its existence highlights how the size of animals can change dramatically due to ecological factors. Large reptiles dominated the landscape then, and the fearsome Titanoboa ruled the waterways as a top predator. While the explicit giant insects may no longer prowl our planet as they did millions of years ago, their legacy invites us to ponder the Earth's evolution and the changing parameters that gave rise to such colossal creatures. As we study the fossil records, we gain a profound appreciation for the biodiversity that once existed and the fascinating ways in which life adapts in response to environmental transformations. The Meganeura, a prehistoric insect that roamed the skies during the Carboniferous period, is fascinating for many reasons, but its impressive size captures the imagination. This dragonfly-like creature, with wingspans reaching nearly 2.5 feet, thrived in an era roughly 300 million years ago when the Earth's atmosphere was rich in oxygen. Scientists believe that this higher concentration of oxygen played a crucial role in allowing insects like Meganeura to grow to such colossal proportions. Insects breathe through a network of tiny tubes known as tracheae, which deliver oxygen directly to their tissues. As the oxygen levels in the atmosphere increased, these systems became more efficient, facilitating larger body sizes. Unlike mammals, which rely on lungs for breathing, insects can absorb oxygen directly through their exoskeletons. This unique respiration method meant that Meganeura could flourish in this oxygen-rich environment without the constraints faced by larger terrestrial animals. The abundant plant life of the Carboniferous period also played a significant role in Meganeura's survival. The lush forests provided not just shelter, but an ample food supply, consisting of smaller insects and perhaps other organic matter. This abundant food source, coupled with a lack of large predators, created an ideal setting for the growth and proliferation of such large insects. In this thriving ecosystem, the Meganeura capitalized on its size to be an effective hunter in the insect world. Finally, the dynamics of evolution during this period favored the development of larger body sizes. With fewer competing species and the advantages provided by their size, insects like Meganeura became prominent aerial predators. Their existence serves as a reminder of the fantastic evolutionary experiments that have occurred on Earth and the intricate connections between atmospheric conditions, ecological niches, and the life forms that inhabit them. The story of Meganeura is not just about size, it's a reflection of a dynamic planet, ever-evolving and full of surprises. The Arthropleura, a giant millipede-like creature that roamed the Earth during the Carboniferous period, is a fascinating glimpse into prehistoric life. This remarkable creature could grow up to 8 feet long, making it one of the largest terrestrial arthropods ever to exist. Its sheer size alone would have made it a formidable presence in its environment, dwarfing many small predators and rivals of its time. Imagine this colossal creature lumbering through dense primeval forests, an unsettling sight for anything that crossed its path. An important characteristic of the Arthropleura was its robust exoskeleton. This tough external covering not only provided protection from potential predators, but also gave it the strength to navigate through its habitat. With a segmented body that allowed for flexibility, it could easily maneuver through the thick vegetation, even in search of food. As a detritivore, it played a crucial role in its ecosystem, feeding on decaying plant matter and recycling nutrients back into the soil. Arthropleura's adaptations extended beyond its size and armor. It possessed numerous legs, typically more than 30, which enhanced its ability to traverse uneven terrain and climb over obstacles. This multitude of limbs contributed to its agility, allowing it to navigate the forest floor with ease. Additionally, its ability to thrive in a high-oxygen atmosphere, a hallmark of the Carboniferous period, enabled it to grow larger than many of its modern relatives, which are significantly smaller due to lower oxygen levels today. Lastly, the Arthropleura's reproductive strategies may have added to its formidable presence. It likely utilized a strategy of laying numerous eggs, which increased the chances of survival for its offspring. The combination of size, strength, adaptability, and successful reproduction made Arthropleura a dominant force in its ecosystem. In its time, this impressive creature was not just a survivor, but a key player in the complex interactions of its prehistoric environment. Giant insects, Fascinating relics of Earth's ancient past thrived in a variety of environments that were richly diverse. During the time of their prominence, particularly in the Carboniferous and Permian periods, which spanned from about 300 to 250 million years ago, the planet was significantly different from today. Among the primary habitats for these colossal creatures were lush, verdant forests, which provided both food and shelter. These ancient forests were a mosaic of gigantic ferns, towering club mosses, and primitive seed plants. The dense foliage and humidity created an ideal environment for insects to grow larger than any we see today. In the absence of birds and mammals that currently compete for these ecological niches, insects flourished, taking advantage of the plentiful vegetation and favorable conditions. Swamps also played a crucial role in the lives of these giant insects. The warm, moist environments of wetlands supported an abundance of decaying organic matter, which fueled the growth of large vegetation and provided ample food sources. Dragonflies with wingspans reaching nearly 2.5 feet soared over these waters, preying on smaller insects that thrived in the humid air. The unique combination of warmth and moisture allowed these insects to maintain their size, as larger bodies tend to lose heat more slowly. Plains and open areas were not as common for giant insects, but they did occasionally inhabit these regions where food sources were available. The expanses of grasses and other plants would have sustained some species, allowing them to move between forested areas and open terrains. Ultimately, the variety of habitats, from dense forests to sprawling swamps, was pivotal in supporting the diverse and larger-than-life insect life of our planet's past. The landscape and vegetation types have played a crucial role in the evolution of insects throughout history. Various environmental factors, such as the availability of food sources, climate conditions, and the physical structure of habitats, have shaped the ways in which insects adapt and thrive. For instance, dense forests with ample foliage can lead to the development of insects with camouflage, allowing them to blend into their surroundings and avoid predators. This adaptation enhances their chances of survival and reproduction. In addition to camouflage, the types of vegetation available can influence feeding behaviors. Insects that feed on specific plants often evolve alongside them, leading to intricate relationships known as coevolution. Consider the relationship between caterpillars and their host plants. Caterpillars may develop specialized mouthparts to effectively eat certain leaves, while the plants might develop toxins to deter such feeding. This dynamic interplay not only affects the insect's physical traits, but can also dictate their behavioral strategies. Moreover, changes in the landscape, such as the emergence of grasslands or the transformation of forests into urban areas, will push insects to adapt or migrate. For example, as woodlands decline and grasslands expand, insects may evolve to develop traits that help them better thrive in open, sunlit areas. This has significant implications for biodiversity, as it can lead to the extinction of species unable to adapt quickly enough to new environments. Finally, the impact of climate cannot be overlooked. Climate change alters vegetation distribution, influencing the rich tapestry of landscapes in which insects live. As temperatures rise and precipitation patterns shift, insects must either adapt to these new conditions or face decline. The interplay of landscape, vegetation, and climate is a complex puzzle that continues to shape the biodiversity of insects, showcasing their remarkable capacity for resilience and change. Giant insects once roamed the Earth during the Carboniferous period, an era remarkably different from today. These colossal creatures thrived in a lush environment characterized by high atmospheric oxygen levels, reaching around 35%. This abundance of oxygen allowed insects to grow to enormous sizes as their unique respiratory system, leading to gas exchange through small openings in their exoskeleton, was effective at transporting oxygen to their tissues. However, despite their impressive size, giant insects face significant environmental pressures. One major challenge was the availability of food. Being larger meant a greater demand for energy, which required them to consume vast quantities of plant material. Fluctuations in plant life and changing climates would have tested their adaptability and forced them to develop efficient foraging strategies to meet their nutritional needs. Another critical pressure was predation. As these creatures grew larger, they naturally became more vulnerable to predators. The evolutionary arms race meant that both prey and predators had to adapt continuously. Giant insects likely developed protective strategies such as tougher exoskeletons and perhaps even speedier movements to evade larger carnivores. Additionally, some species may have evolved camouflage or specialized behaviors to remain hidden from view. Lastly, environmental conditions, including temperature and moisture levels, would have played a significant role in shaping their survival strategies. Extinction events, such as severe climate changes that reduced oxygen levels and altered habitats, posed existential threats. Those that adapted to these changing landscapes, possibly by developing new reproductive strategies or discovering new niches, were more likely to thrive, leaving behind a fascinating legacy that still sparks curiosity among scientists today. The history of Earth's atmosphere is a fascinating tale of change, especially regarding oxygen levels. Over the span of millions of years, fluctuations in atmospheric oxygen have had significant effects on the evolution of various life forms, particularly insects. Some periods, like the Carboniferous era, were marked by oxygen levels that were much higher than what we experience today, often reaching upwards of 35% compared to the current 21%. This abundant oxygen supply allowed for larger body sizes in insects, a phenomenon scientists refer to as gigantism. With more oxygen available, insects could sustain their larger bodies through the process of respiration. Unlike mammals, insects breathe through a network of tubes called tracheae that directly deliver oxygen to their tissues. Higher levels of oxygen meant that these tubes could efficiently supply the energetic demands of larger body sizes, paving the way for massive insects, such as the giant dragonfly-like Meganeura, which had wingspans of nearly 2 feet. Conversely, during periods when oxygen levels dropped, these enormous insects decreased in size. The Permian-Triassic extinction event, for example, which saw a significant drop in oxygen levels, coincided with the decline of many large insect species. As the atmosphere became less conducive to sustaining larger body structures, natural selection favored smaller, more efficient organisms that could thrive with limited oxygen availability. Today, while most insects are significantly smaller than their prehistoric relatives, studying this relationship between oxygen levels and insect sizes provides valuable insight into the complexities of evolution and ecology. It underscores the intricate connections between atmospheric conditions and biological diversity, showing us how even slight changes in the environment can dramatically shape life on Earth. Scientists have long been fascinated by the relationship between oxygen levels and the size of insects, a topic that offers intriguing insights into evolution and biology. Over the years, a variety of experiments have explored this connection, often focusing on how increased oxygen availability might have contributed to the larger sizes of some prehistoric insects. One notable line of investigation involved recreating ancient atmospheric conditions in controlled environments. For instance, researchers have adjusted oxygen levels in laboratory settings to mimic those of the Carboniferous period, around 300 million years ago, when insects such as dragonflies reached wingspans of up to 2 feet. By raising the oxygen concentration in these environments, scientists observed that certain species of modern insects exhibited significant increases in size and altered metabolic rates, suggesting a clear link between oxygen availability and insect growth potential. Field studies have also provided valuable data. Observations of extant insect populations in areas with varying oxygen levels, such as high altitudes versus sea level, have shown correlations between oxygen concentration and insect size. Insects living at high elevations, where the air is thinner and oxygen levels are lower, tend to be smaller, while those in denser environments can grow larger. This geographic variation has helped hone the understanding of how oxygen influences not just individual species, but entire ecosystems. In addition, Genetic studies have illuminated the physiological adaptations insects undergo in different oxygen environments. Some species develop larger tracheal systems which transport oxygen throughout their bodies, allowing them to thrive in low oxygen settings. These findings not only aid in understanding insect evolution, but also provide a greater comprehension of how life on Earth adapts to changing environmental conditions. As scientists continue to investigate these relationships, they uncover more about the remarkable interplay between oxygen and the extraordinary diversity of life forms. To understand how a return to high oxygen levels might impact insect growth today, we need to take a brief journey back in time. During the Carboniferous period, approximately 300 million years ago, oxygen levels in Earth's atmosphere soared to around 35%, compared to the 21% we experience today. This abundance of oxygen created a remarkable environment for insects, enabling them to grow to massive sizes. Some species, like the dragonfly relatives of that era, boasted wingspans nearing 2.5 feet. One of the primary reasons insects grew so large during these high oxygen times is their unique respiratory system. Unlike mammals that have lungs, insects breathe through a network of tiny tubes called tracheae that deliver oxygen directly to their tissues. This system allows for efficient oxygen distribution, but its efficiency is heavily dependent on the concentration of oxygen in the atmosphere. With more oxygen available, the potential for larger body sizes and increased metabolic rates would be significantly enhanced. In today's world, if oxygen levels were to rise again to those historical heights, we could witness a revival of these giant insects. The additional oxygen could enable contemporary insect species to expand in size, potentially leading to a whole new range of ecological interactions. Larger insects might become more formidable predators or even alter pollination processes, thereby affecting entire ecosystems. These changes could also influence human activities and agricultural practices, since larger insects might impact pest control and pollination efficiency. However, the effect of increased oxygen is not just about size. It could also lead to faster growth rates and altered life cycles among many species. Shorter generations might allow for quicker adaptations to environmental changes, ultimately reshaping biodiversity. While a return to those high oxygen levels might initially sound like an incredible prospect, the implications would ripple across ecosystems and human life in ways that challenge our current understanding. The past echoes in the present, reminding us of the intricate web of life shaped by the very air we breathe. Throughout history, insects have astounded scientists with their fascinating behaviors and complex social structures. A remarkable area of study is that of giant insects, which often capture our imaginations in popular culture. These larger-than-life creatures, while exaggerated in movies and literature, offer real insights into the evolutionary adaptations of insects and their social dynamics. Recent studies have focused on understanding how these giants, such as certain species of cockroaches and beetles, interact within their environments and with each other. Researchers have discovered that certain traits common in smaller insects, like teamwork and communal living, are often amplified in their larger relatives. For example, giant ants, which can grow to several centimeters in length, showcase advanced social behaviors, including cooperative foraging and complex nest-building techniques, which highlight their organizational prowess. Moreover, the study of giant insects provides a unique lens into the principles of biomechanics. Their larger size presents different challenges, such as weight and mobility, leading scientists to explore how these creatures have evolved specialized structures to support their bodies. Understanding how giant insects move and survive not only enlightens us about their biology, but also offers vital clues about the environmental conditions of the ancient Earth when they thrived. The insights gleaned from studying giant insects extend beyond pure biology, opening discussions about biodiversity and conservation. As we learn more about these impressive creatures, we recognize their role in their ecosystems and the importance of preserving the habitats that allow their extraordinary social structures and behaviors to flourish. Thus, the exploration of giant insects continues to invite curiosity, combining wonder with a deeper understanding of life on our planet. Insects have developed a fascinating array of communication methods that enable them to maintain social structures and coordinate activities within their colonies. One of the most common forms of communication among insects is through chemical signals, known as pheromones. These substances are released into the environment and can convey vital information, such as alarm signals, food sources, or the presence of a mate. For instance, when a honeybee discovers a rich source of nectar, it can emit a specific pheromone that alerts other bees in the hive to the location of this valuable food. In addition to chemical communication, insects also utilize sounds as a means to relay information. This can be observed in crickets, which produce distinct sounds by rubbing their wings together, a behavior known as stridulation. The sounds can attract potential mates or warn others of threats. Similarly, some species of cicadas are infamous for their loud calls that can be heard over great distances, which serve to attract mates, particularly during their mating seasons. Visual signals play an equally crucial role in insect communication, especially among species that rely on visual cues to find mates or establish territory. Fireflies are a prime example, as they use bioluminescence to produce specific light patterns that signal their presence to potential partners. Ants, on the other hand, can communicate through body movements or postures, which can indicate aggression or submission, helping to maintain order within their densely populated colonies. These various forms of communication underscore the complexity of insect societies. Whether through chemical, auditory, or visual means, insects have evolved remarkable strategies to connect with one another, ensuring their survival and the success of their communities. This intricate web of interactions not only allows them to thrive in diverse environments, but also reveals the sophisticated nature of these seemingly simple creatures. Giant insects, an intriguing aspect of our planet's ancient ecosystems, likely exhibited a variety of mating rituals and reproductive strategies far different from what's seen in today's smaller insect populations. The sheer size of these creatures would have influenced their behaviors, environmental adaptations, and social structures in fascinating ways. One of the significant reproductive strategies might have involved elaborate courtship displays. Much like modern-day peacocks or certain bird species, giant insects could have utilized vibrant colors, intricate movement patterns, or even pheromone releases to attract mates. The rituals could range from choreographed dances to the use of bioluminescence, potentially attracting others through mesmerizing light displays in the dim, prehistoric environments. In terms of mating practices, some giant insects may have engaged in mate guarding, where males would fiercely protect their chosen female from rivals. This behavior would ensure not only reproductive success, but also the survival of their genetic material. Additionally, giant insects might have adapted brood care strategies, where both parents or even specific groups within their species took turns protecting and nurturing their offspring, enhancing the chances of survival in a world of predators. Moreover, the physical size of these insects could have prompted unique reproductive adaptations. For instance, laying large quantities of eggs may have been essential to ensure enough young survive to adulthood. Nesting behaviors could have included creating elaborate structures to protect these eggs, showcasing an evolution of intelligence and social cooperation among these formidable ancient invertebrates. As we continue to study the fossil records and compare them with modern insects, we uncover more about the complex lives of these colossal creatures and their remarkable strategies for survival. Giant insects have intrigued scientists for centuries, and their existence offers a fascinating glimpse into the evolutionary past. One of the most notable periods where these enormous creatures thrived was during the Carboniferous period, around 300 million years ago. Atmospheric conditions back then featured higher oxygen levels, which allowed insects to grow much larger than those we see today. For instance, fossil evidence shows dragonflies with wingspans of nearly 2.5 feet, a stark contrast to the size of modern species. Studying these giant insects helps scientists understand the relationship between environmental factors and evolutionary adaptations. As oxygen levels have fluctuated over geological time, researchers can observe how these changes influence insect physiology and their potential for growth. The size increase in ancient insects also underscores the limits of physical and biological constraints. We learn that there are practical boundaries that living organisms must navigate in response to their environments. Additionally, the fossil record of these large insects sheds light on their predatory behaviors, interactions with other species, and their ecological niches within ancient ecosystems. Exploring the remnants of these creatures provides a unique window into ancient food chains and how they may have shaped biodiversity long ago. This information informs our understanding of evolutionary pressures and gives insight into the dynamics of natural selection. Finally, the study of giant insects extends beyond mere curiosity. It serves as a key lesson in the broader scope of evolutionary biology. By examining how these massive creatures adapted or failed to adapt to their changing environments, scientists glean invaluable insights that resonate even today. This ongoing research informs our understanding of how current insects might evolve in response to climate change, showcasing an intricate connection between our environment and the living world. Prehistoric creatures, often referred to as ancient animals, offer profound insights into the remarkable adaptability of life on Earth. By studying fossils and the evidence left behind, scientists unveil the stories of how these creatures thrived in dramatically changing environments. Each era brought its own set of challenges, from shifting climates to catastrophic events, and these organisms had to navigate these changes or face extinction. One captivating example comes from the dinosaurs, which dominated the planet for over 160 million years. Their ability to adapt to various habitats, from lush forests to arid deserts, showcases the incredible versatility of life. Some evolved into enormous, long-necked giants, while others became small, agile creatures. Their legacy even lives on today in the form of birds, who are the direct descendants of certain theropod dinosaurs. This continuous thread highlights how survival often hinges on the capacity to evolve and adapt through generations. Another fascinating group to consider is the early marine life, such as trilobites and ammonites. These creatures inhabited the oceans for millions of years, demonstrating an exceptional ability to adapt to varying oceanic conditions. They survived mass extinction events which wiped out a significant portion of life in the seas, and their subsequent evolution illustrates how life can rebound and re-establish itself in the wake of disaster. Ultimately, the history of these prehistoric beings is an ongoing testament to life's resilience. They remind us that adaptability is a cornerstone of survival. With each new challenge presented by the Earth's ever-changing environment, life has not only endured but has flourished, reflecting the incredible potential for evolution and the endless possibilities that lie within the tapestry of existence on our planet. Giant insects, those remarkable creatures that roamed the Earth millions of years ago, offer a fascinating glimpse into the principles of natural selection. During the Carboniferous period, which lasted from about 359 to 300 million years ago, atmospheric oxygen levels were significantly higher than they are today. This abundance of oxygen enabled insects to grow to impressive sizes as they relied on diffusion to breathe. The larger their bodies, the more oxygen they could absorb through their exoskeletons, granting them a distinct survival advantage. Natural selection operates on the premise that individuals with traits that enhance their chance of survival and reproduction are more likely to pass those traits to future generations. In the case of these giant insects, size could have played a crucial role in evading predators, finding mates, and competing for resources. Predators are often less agile when faced with larger prey. Thus, the immense size of these insects may have conferred significant survival benefits, allowing them to thrive in their ecosystems. However, factors such as environmental changes and competition also illustrate natural selection's dynamic nature. As the atmosphere gradually shifted, oxygen levels dropped, making it increasingly difficult for larger insects to sustain their size. Alongside this shift, the evolution of birds and mammals introduced new predation pressures. Over time, those insects that did not adapt to these changing conditions were less likely to survive and reproduce, showcasing the ever-evolving dance of natural selection. Today, we can observe remnants of those giant insects in our smaller modern relatives. Cockroaches and dragonflies, while no longer titans of the air, still exhibit traits influenced by their ancient ancestors. The principles of natural selection are not just historical curiosities. They continue to shape the life forms that exist on our planet, reminding us of the intricate tapestry of evolution woven over millions of years. The fascination with giant insects has inspired both digital and physical reconstructions that allow us to envision these creatures, particularly from prehistoric times when some were significantly larger than their modern-day counterparts. These reconstructions often draw on fossil evidence, which helps scientists and artists alike to create lifelike representations of these ancient life forms. Digital reconstructions utilize advanced computer graphics and modeling software to simulate the appearance and behavior of giant insects. Through these techniques, paleontologists can recreate insects such as the Meganeura, a dragonfly-like creature with a wingspan of nearly 2 feet. By analyzing fossilized remains, researchers can suggest what these insects may have looked like, including their coloration and texture, creating an immersive experience that brings history to life. Virtual reality experiences and documentaries often rely on these detailed models, allowing viewers to explore the world of these giants in a strikingly realistic manner. In the realm of physical reconstructions, scientists and artists have taken on the challenge of building life-sized models of giant insects for educational purposes and museum exhibits. These sculptures are often made using various materials, from lightweight plastics to more durable rending materials, designed to capture the size and intricate features of the insects. For example, a recreation of a giant prehistoric millipede might highlight its segmented body and numerous legs, conveying both the awe and the peculiarities of these ancient creatures. These visualizations not only serve a scientific purpose, but also engage the public's imagination. They invite us to ponder the ecological conditions of the past, such as higher oxygen levels that allowed these incredible insects to thrive. The blends of art and science in these reconstructions also prompt discussions on evolution, adaptation, and the wonder of biodiversity, reminding us of the vast array of life that once ruled our planet. Reconstruction of historical events, peoples, or environments serves as a crucial tool for illuminating the past. By piecing together fragments of knowledge through archaeological finds, ancient texts, and early artworks, scholars gain a clearer view of how civilizations interacted with one another and with their surroundings. This process goes beyond mere curiosity. It provides context and depth to our understanding of human progression and cultural evolution. For instance, when researchers reconstruct ancient landscapes, they can reveal how early communities adapted to changes in climate and geography. Such insights help explain why certain societies flourished while others diminished over time. Understanding these dynamics not only offers a glimpse into daily life during those eras, but it also informs us about the resilience and ingenuity of the human spirit in overcoming challenges. Furthermore, reconstructions allow us to explore the interconnectedness of various cultures. The trade routes established thousands of years ago, for example, facilitated not just commerce, but the exchange of ideas, art, and technologies. By reconstructing these networks, historians can elucidate how influences traveled across regions, shaping the civilizations involved, often in unexpected ways. Ultimately, these reconstructions invite us to reflect on our own place in the timeline of history. They remind us that current societies, like those of the past, are shaped by a complex interplay of environmental, social, and cultural factors. By learning about how previous generations navigated their realities, We gain valuable insights that can inform our decisions today, ensuring that history remains a living dialogue with the past. The recreations of cosmic events, celestial bodies, and even entire galaxies have come a long way, thanks to advances in technology over the past few decades. In the earlier days of cosmology, astronomers relied heavily on observational data through telescopes, which provided limited, often grainy images of the universe. These images were notoriously difficult to interpret, and scientists had to rely on their imagination and basic principles of physics to fill in the gaps. As technology progressed, so did our ability to simulate the cosmos accurately. High-resolution spacecraft instruments, like those carried by the Hubble Space Telescope, have given us stunningly detailed images of distant galaxies, nebulae, and star formations. Furthermore, computer simulations have become sophisticated enough to recreate cosmic phenomena with incredible fidelity. Leading-edge algorithms can model the dynamics of galaxies forming, merging, and evolving over billions of years, allowing scientists to visualize processes that are otherwise impossible to observe directly. Moreover, advances in machine learning and artificial intelligence are taking these recreations to new heights. By analyzing vast amounts of data, these technologies can help identify patterns and predict cosmic events with a level of precision previously unattainable. For instance, we can now foresee certain celestial occurrences, such as supernovae or gravitational waves, with remarkable accuracy, and simulate what they might look like. This has not only enhanced our understanding, but has also enabled a more interactive experience, bringing the universe closer to us than ever before. As we venture deeper into the cosmos, the evolution of these recreations continues to unfold. With upcoming missions, like the James Webb Space Telescope, we can expect an even more comprehensive understanding of celestial phenomena. Every advancement invites us to rethink our place in the universe, giving rise to fresh questions and igniting a sense of wonder that has been part of human curiosity since time immemorial. The journey through the stars is not merely about the facts, it's about the stories they tell and the connections we build with the cosmos. The ancient world was a realm of remarkable biodiversity, particularly during the era when dinosaurs roamed the earth. This was also a time when giant insects flourished, showcasing a fascinating interplay between these invertebrates and their larger vertebrate counterparts. Some of the largest insects known to have existed, like the dragonfly-like Meganeura and the massive scorpion-like Arthropleura, thrived during the Carboniferous and Permian periods, long before dinosaurs appeared. However, different insect species persisted through various geological periods, and many coexisted with the dinosaurs. Insects and dinosaurs filled complementary ecological roles, with insects primarily serving as decomposers, pollinators, and food sources. Their existence positively impacted the plant life around them, which in turn supported the large herbivorous dinosaurs. As plants flourished, so did the insects that relied on them for nourishment. This symbiotic relationship illustrates how life in ancient ecosystems was interconnected, highlighting the delicate balance of life forms at that time. It's important to note that while some insects were indeed massive, they were still quite small relative to the more dominant creatures of their time. Most insects cohabited in the same spaces as dinosaurs without posing significant threats to them, although larger predatory insects may have occasionally hunted smaller vertebrates like baby dinosaurs or other soft-bodied creatures. The sheer variety of insects likely provided a source of sustenance for numerous species within the dinosaur community. Intriguingly, the adaptability of insects played a crucial role in their survival alongside dinosaurs, allowing them to exploit various niches in their environments. From scavenging carcasses to thriving in the canopies of ancient forests, these insects mirrored the evolutionary success of dinosaurs, demonstrating that even the most gigantic creatures coexisted with smaller, yet equally fascinating forms of life. This rich tapestry of existence continues to intrigue scientists and underscores the complexity of ecosystems throughout history. During the late Paleozoic and Mesozoic eras, the Earth witnessed a remarkable array of life forms, including giant insects and dinosaurs, both of which played significant roles in shaping their ecosystems. The presence of gigantic insects can largely be attributed to higher atmospheric oxygen levels during these periods. With atmospheric oxygen concentrations estimated to be around 35%, some insects, like dragonflies, evolved wingspans of more than 2 feet. These enormous insects occupied various ecological niches, functioning as both predators and prey. As predators, massive insects were key players in controlling populations of smaller organisms and influencing the food chain. They could take down small vertebrates while also serving as a food source for larger prehistoric creatures. Their diverse body sizes and forms allowed them to exploit different habitats, from lush, swampy areas to dense prehistoric forests. This diversity supported a complex food web, fostering an environment rich in species. Dinosaurs, on the other hand, were the dominant terrestrial vertebrates of the Mesozoic era, displaying a stunning variety of shapes and sizes. Herbivorous dinosaurs transformed landscapes by consuming vast quantities of plant life, which affected plant community structures and promoted new growth. Their grazing would lead to a dynamic equilibrium where both flora and fauna thrived, contributing to the overall health of ecosystems. Together, these two giant groups of prehistoric beings created a fascinating interplay within their ecosystems. The enormous insects provided a link between the plant life and the larger dinosaurs, while the dinosaurs, through their varied diets and behaviors, shaped their environments in profound ways. Thus, the coexistence of giant insects and dinosaurs illustrates a critical chapter in the history of life on Earth, showcasing how diverse organisms can collectively influence and sustain intricate ecosystems. Paleontologists have developed fascinating theories about the interactions among prehistoric creatures based on fossil evidence and the environments in which these creatures lived. One of the most intriguing interactions is the predator-prey relationship. Take the towering Tyrannosaurus rex, for example. This formidable dinosaur likely hunted large herbivores like Triceratops. By studying the wear patterns on teeth and the evidence of bite marks on bones, scientists can piece together a vivid picture of these life and death encounters. But it's not just about hunting and being hunted. There is also evidence suggesting that some creatures engaged in scavenging behavior. For instance, smaller carnivorous dinosaurs or scavengers might have followed larger predators, waiting for an opportunity to feast on leftover carcasses. This highlights a complex web of interactions where survival often meant seizing upon the remnants of another's hard-fought meal. Some paleontologists have proposed theories on symbiotic relationships as well. For example, certain species of smaller dinosaurs or ancient reptiles may have had mutualistic relationships with larger ones, perhaps cleaning parasites off their skin or feeding on remnants left behind during feeding. This potential cooperation would illustrate that even in the harsh realities of prehistoric life, some species found ways to coexist and support each other. In addition to these direct interactions, fossil evidence also points to the impact of environmental changes on creature interactions. As some species thrived and others faced extinction due to climatic shifts, the dynamics of predator and prey or competition for resources evolved dramatically over time. These interactions, while drawn from ancient history, give us incredible insight into the complexity of life on Earth and the interconnectedness of different species, painting a broader picture of ancient ecosystems and the roles played within them. Giant insect fossils often capture the imagination, offering a glimpse into Earth's distant past. Much of this preservation occurs in amber, a fossilized tree resin. When insects became trapped in the sticky resin, they were effectively sealed off from the environment, protecting them from decay. Over time, the resin hardened into amber, encasing the insects in a time capsule that can be millions of years old. This natural process is crucial. Without it, these delicate creatures would have likely disintegrated long before the present day. Excavating these fossils poses unique challenges. The first hurdle is locating amber deposits, which often requires extensive fieldwork in specific geological areas. This can be a painstaking process because amber can be buried deep in sediments or hidden among other natural materials. Once a site is identified, researchers must carefully extract the amber without breaking it, as the fossils within can be incredibly fragile and vulnerable to damage. Additionally, once the amber is extracted, researchers face the task of carefully preparing the specimens for study. This involves cleaning and sometimes cutting the amber to expose the insects without harming them. Each cut demands precision, as the wrong move could obliterate valuable data that scientists extract from these fossils, such as their age and evolutionary significance. Furthermore, there is an ongoing debate within the scientific community about the implications of finding such well-preserved specimens. Although they provide insights into ancient ecosystems, they also raise questions about how life evolved and adapted over millions of years. The challenges of excavation and preservation are thus not merely physical, but also intellectual, enriching our understanding of life on Earth. Ensuring the integrity of fossils during study and transport involves a series of meticulous measures designed to protect these irreplaceable artifacts from damage. One of the first steps is the careful excavation of fossils, where paleontologists use specialized tools to gently unearth specimens. The goal is to minimize exposure to environmental factors that could degrade the fossil, such as changes in temperature or humidity. Each specimen is documented thoroughly, noting its location and the surrounding geological context, which is vital for understanding its history and significance. Once a fossil is extracted, it is often encased in a protective material. This material can be a specially formulated plaster or a rigid foam that surrounds the fossil to provide stability and support. The aim is to absorb shocks during transport and prevent fractures or breaks. Each fossil is secured in a manner that allows for airflow, preventing mold and decay while still providing a protective barrier. Transporting fossils requires careful planning, especially if the specimens are particularly large or delicate. Fossils are usually transported in climate-controlled environments to avoid any harmful effects from fluctuating temperatures or humidity. Vehicles used for transportation are often specially equipped to handle fragile loads, with features that mitigate vibrations and jostling during transit. When fossils arrive at a research facility or museum, even greater caution is exercised. They are unpacked in controlled environments with specialists on hand to monitor their condition. Additionally, modern technology such as imaging and scanning helps scientists assess any internal damage or structural issues that may not be visible to the naked eye. This comprehensive approach ensures that these precious windows into our planet's past remain preserved for future generations to study and enjoy. Determining the age of giant insect fossils is a fascinating process that combines several scientific techniques. Scientists often begin their exploration with a method called radiometric dating. This technique relies on the decay of radioactive isotopes, which are unstable forms of elements that transform into stable ones over time. For fossils, the most commonly used isotope is carbon-14, particularly for more recent specimens. However, in the case of insect fossils that are millions of years old, scientists tend to use isotopes like uranium and thorium to date the surrounding sedimentary rock instead, since these creatures thrived long before the era of carbon-14 dating. Another important method is biostratigraphy, which involves studying the layers of sedimentary rock in which the fossils are found. Fossils occur in specific layers, or strata, that correspond to particular geological time periods. By identifying the types of other fossils present in the same strata, scientists can deduce a time frame for when the giant insects lived. This technique is especially useful in correlating findings from different locations, creating a more comprehensive timeline of life on Earth during various epochs. Moreover, some scientists rely on paleomagnetic dating, which examines the alignment of magnetic minerals in volcanic or sedimentary rocks. Over geological time, Earth's magnetic field has reversed its polarity, and the evidence of these changes is recorded in rocks. By matching the magnetic signature of the rocks containing the fossils to known patterns, researchers can determine when those rocks were formed, thus providing an age for the insect fossils. So, through a combination of radiometric dating, biostratigraphy, and paleomagnetic analysis, scientists pieced together a more accurate picture of when giant insects roamed our planet. This multidisciplinary approach not only reveals the age of these remarkable fossils, but also deepens our understanding of the ecosystems they thrived in, showcasing Earth's dynamic history. The story of giant insects is inextricably linked to the Earth's ancient climate changes, particularly during the Paleozoic era, millions of years ago. During this time, the planet was a vastly different place. Ocean levels were higher, the atmosphere was rich in oxygen, and lush forests stretched across the land. These conditions were conducive to a remarkable diversity of life, including insects that grew to astonishing sizes. Some dragonflies during this era boasted wingspans exceeding 2 feet, thanks largely to an abundance of oxygen that allowed for more robust development. As the climate began to shift, changes in temperature and atmospheric composition had far-reaching effects on these giant creatures. For instance, during periods when the Earth cooled, forests shrank, and habitats were lost, leading to increased competition for resources. Additionally, the cooling temperatures may have caused a decline in insect size, as the metabolic needs of larger animals could not be met in a rapidly changing climate. Scientific studies suggest that temperature extremes might have restricted the growth potential of insects, contributing to their gradual decline in size over time. Moreover, the extinction events that punctuated the Earth's history also played a significant role in determining the fate of these giant insects. With the arrival of major extinction events, such as the Permian-Triassic extinction, around 90% of marine species and 75% of terrestrial species disappeared. These catastrophic shifts resulted in a drastic reduction in biodiversity, along with a significant impact on ecosystems where these majestic giants had once thrived. The subsequent rise of new types of animals, like smaller mammals and birds, created an environment that was less favorable for the survival of colossal insects. The evolution and eventual extinction of giant insects were deeply influenced by the climate dynamics of our planet. As conditions changed and habitats transformed, these once mighty creatures faced increasing challenges that ultimately led them to shrink in size and diminish in numbers. The story of these ancient giants serves as a reminder of the intricate connections between climate, evolution, and extinction, a narrative that continues to unfold throughout the history of life on Earth. Scientists studying the relationship between climate shifts and the size of ancient insects use a fascinating range of evidence drawn from fossil records, paleoecological data, and the principles of biology. One of the key pieces of evidence comes from understanding the changes in temperature and oxygen levels throughout Earth's history. Insects breathe through a system of spiracles and tubes, and their growth is significantly affected by the availability of oxygen. During warmer periods in the Earth's past, particularly the Carboniferous and Permian periods, higher oxygen levels enabled insects to grow larger. Researchers often examine fossilized remains of insects, which can provide direct insight into their size and morphology. These fossils can be found in sedimentary rock layers that have accumulated over millions of years. By dating these layers and correlating them with known climate shifts, scientists can establish a timeline of changes in insect size. For example, the famous giant dragonflies of the Carboniferous period, with wingspans reaching nearly 2 feet, are attributed to the combination of high oxygen levels and warmer temperatures during that epoch. Moreover, scientists analyze isotopic data from these ancient sediments, which can reveal past atmospheric conditions. The presence of certain isotopes can indicate shifts in climate, such as warming periods or ice ages. By correlating these isotopic records with insect fossil sizes, researchers can identify trends that suggest larger insects thrived during specific climate conditions, while smaller sizes appeared during cooler periods. In addition to fossils and isotopic analysis, modern studies also use computer models to simulate the effects of climate changes on insect growth patterns. This multifaceted approach allows scientists to better understand not just the size of ancient insects, but also the broader implications for ecosystems and biodiversity in a changing climate. Each of these pieces of evidence paints a compelling picture of how climate has shaped the evolution of life on Earth, including its incredible insects. The relationship between vegetation and insects is a fascinating one that has evolved significantly over millions of years. As plants changed, whether due to climate shifts or other environmental factors, the species of insects that inhabited those areas adapted to the new conditions. These adaptations influenced not only their survival, but also the overall ecological balance of their habitats. During early periods of Earth's history, vast forests of ferns and cycads dominated the landscape. Insects, like early beetles and moths, thrived in these lush environments, developing specialized feeding habits and reproductive strategies to take advantage of the abundant plant life. As flowering plants emerged during the Cretaceous period, a remarkable transformation occurred. Insects rapidly evolved alongside these new, diverse plant forms, which provided different food sources and shelter. This coevolution facilitated a rich diversity of insect life, leading to a boom in species that could pollinate flowers and utilize nectar. As vegetation continued to evolve through periods of glaciation and climate change, insects exhibited remarkable adaptability. For instance, in regions where forests receded, some insects shifted to more arid habitats, while others found refuge in pockets of vegetation that persisted. This resilience reflects not only their ecological importance, but also their evolutionary success. The ability of insects to occupy various niches allowed them to thrive in changing environments, showcasing a dynamic interplay between flora and fauna. Today, as we face further environmental changes due to human activity, these intricate relationships are again at risk. Alterations in vegetation caused by urbanization, deforestation, and climate change disrupt historical habitats that insects have adapted to over millennia. Understanding the past interactions between vegetation and insects can shed light on the critical role both play in maintaining healthy ecosystems, reminding us of the delicate balance that sustains life on Earth. The study of modern insect behavior and physiology has unveiled fascinating insights into the lives of their prehistoric ancestors. Insects, which have existed for over 400 million years, are incredibly varied and adapted creatures today. By observing the behaviors of contemporary species, scientists can infer characteristics and survival strategies that may have existed in their ancient relatives. For instance, the social structures of bees and ants today shed light on the potential complexities of cooperative behavior in early insect populations. One of the critical revelations comes from examining the anatomy and physiology of insects. The remarkable diversity in the shapes and sizes of limbs, mouthparts, and wings can provide clues about the environmental challenges faced by their ancestors. For example, the specialized mouthparts of certain modern insects suggest adaptations for feeding on specific plants that might have been prevalent in prehistoric ecosystems. This specialization indicates that interactions with flora, such as early flowering plants, played a crucial role in insect evolution. Additionally, molecular studies have helped scientists trace the evolutionary lineage of insects. By analyzing the genetic makeup of modern species, researchers can construct a more refined picture of insect ancestry. These findings reveal patterns of speciation and extinction events that shaped the evolution of insects. Such insights not only inform us about the past, but also help predict how current insects might adapt to rapidly changing environments due to climate change and habitat loss. Insects are remarkable survivors, having thrived through several mass extinction events. The resilience and adaptability displayed by modern insects highlight the evolutionary success of earlier forms. As we continue to uncover the connections between the behaviors and biological traits of today's insects and their prehistoric ancestors, we deepen our understanding of both evolution and the importance of these creatures in our ecosystems. This ongoing research ensures that the story of insects remains as dynamic and engaging as the creatures themselves. Researchers often turn to modern insects to glean insights into the lives of their ancient counterparts, particularly those fascinating giant species that once roamed our planet. The methodology behind this approach involves careful examination of the behaviors, habitats, and physiological characteristics of today's insects. By studying these living representatives, scientists can formulate hypotheses about how similar traits might have functioned in the past. One of the most striking examples is found in the study of giant dragonflies, which lived during the Carboniferous period roughly 300 million years ago. These ancient creatures, with wingspans that could exceed 2 feet, have left fossilized evidence that researchers compare to modern dragonfly species. By observing how contemporary dragonflies hunt, mate, and migrate within similar environments, scientists can infer how their gigantic relatives might have interacted with the ecosystem of their time. Additionally, researchers explore the evolutionary adaptations that allowed these insects to thrive in prehistoric conditions. For instance, atmospheric oxygen levels during the Carboniferous were significantly higher than today, which likely supported the larger body sizes. Comparing modern insects that thrive in various oxygen levels helps researchers understand the physiological limitations these giant insects faced, offering a lens through which to view the intersection of environment and biology. Finally, the functionality of behaviors observed in living insects helps in piecing together the possible daily life of their gigantic ancestors. For example, examining how modern insects camouflage, hunt, or even respond to predators can provide clues about survival strategies in ancient ecosystems. Through this compelling blend of observation, hypothesis, and fossil evidence, researchers continue to unravel the mysteries of life on Earth before the age of mammals, with modern insects acting as vital keys to understanding the past. The age of giant insects, particularly during the Carboniferous period, has long fascinated scientists. This era, which spanned from around 300 to 360 million years ago, was characterized by higher oxygen levels and lush vegetation, creating the perfect conditions for insects to grow to remarkable sizes. To understand this ancient phenomenon, modern events and phenomena can provide valuable insights. One key modern event is climate change. As temperatures rise and atmospheric conditions shift, we can observe how current insect populations respond to changes in their environments. For example, increasing temperatures can lead to the expansion of certain species while others struggle to survive. By studying how insects adapt or fail to adapt today, scientists can draw parallels with how ancient insects may have flourished during warm periods in the past. Additionally, the study of oxygen levels in our modern atmosphere serves as another important piece of the puzzle. The oxygen concentration during the Carboniferous period was significantly higher than today, reaching levels of about 35% compared to 21% now. Researchers are investigating how varying oxygen levels affect insect physiology and growth. Experiments that raise oxygen levels in controlled environments show that some insects increase in size, hinting that elevated oxygen may play a critical role in the development of giant insects in prehistoric times. Finally, the discovery of fossilized remains and amber deposits helps scientists understand the biology and behavior of ancient species. For instance, modern advances in imaging and genetic analysis allow us to reconstruct the life cycles and environmental interactions of these insects. Fossilized evidence, combined with current ecological studies, paints a clearer picture of how and why these giant insects thrived, shedding light on our planet's evolutionary history and the factors that drove such remarkable sizes. Imagine a world where giant insects roam our landscapes, a concept that has fascinated scientists and authors alike. If insects were to reach gigantic sizes, the first noticeable change would be their impact on ecosystems. Insects play vital roles in pollination, decomposition, and as a food source for many animals. With their increased size, the dynamics of these interactions would shift dramatically. Larger insects could consume more resources, potentially outcompeting smaller species for food and habitats. This competition could lead to the decline or even extinction of some smaller insects. disrupting the delicate balance that nature relies on. Consider, too, the implications for herbivorous and carnivorous species. Larger insects, with their heightened appetites, might devastate vegetation, leading to a loss of plant diversity. As plants struggle to survive, the animals that depend on them for food could face significant challenges. Moreover, predators that typically feast on smaller insects might be forced to adapt. They would need to evolve to hunt these larger creatures, altering predator-prey dynamics almost beyond recognition. Beyond ecological impacts, giant insects could also pose direct threats to human activities. Agriculture might be severely affected as oversized grasshoppers or beetles could wreak havoc on crops. Urban environments would not be immune, as enormous insects could invade homes and pose health risks. Imagine cockroaches the size of cats. Maintenance and pest control would become urgent and complex issues that society would have to address. Yet, despite the potential chaos, we might also discover unexpected benefits. With their ability to consume vast quantities of organic material, these giant insects could help manage waste in agricultural and urban spaces. Like nature's own trash compactors, they could break down refuse more efficiently than their smaller counterparts. Overall, while giant insects could lead to upheavals in both our ecosystems and lifestyles, they might also prompt innovative solutions and adaptations that reflect the remarkable resilience of nature. The presence of giant insects would have a profound impact on today's biodiversity, fundamentally altering ecosystems around the world. Insects play crucial roles in many ecological processes, including pollination, decomposition, and serving as food for various species. If insects were to reach massive sizes, the balance of many ecosystems could shift dramatically. For instance, larger insects would require more resources, which could lead to increased competition among species for food and habitat. The implications of these changes extend beyond just competition. Giant insects could potentially outcompete existing species, leading to extinction among smaller counterparts. Additionally, these enormous creatures would have different predatory behaviors and ecological roles that might disrupt food chains. For example, giant carnivorous insects might emerge, impacting the populations of small mammals and birds and altering predator-prey dynamics across various habitats. On the other hand, the presence of giant insects could also encourage the evolution of other species. Animals that depend on insects for food might adapt to deal with the larger sizes, leading to evolutionary changes among birds, bats, and amphibians, among others. This coevolution could result in entirely new species or adaptations that may not have been necessary in our current ecosystem setup. Finally, humans would also feel the influence of these giant insects. Agricultural practices would need to change, as gigantic pollinators or pest species would challenge farmers and food production systems. The advent of giant insects would lead to a complex web of changes, highlighting the interconnectedness of life and how the presence of a single group of organisms can ripple through the tapestry of biodiversity. The prospect of encountering massive insects presents a fascinating subject for exploration. Should such a scenario become reality, the challenges humans would face could be as daunting as they are varied. First and foremost, the sheer size of these creatures would present immediate physical dangers. Imagine insects many times larger than those we are accustomed to, like a grasshopper the size of a dog. Their strength and agility would dwarf that of people, making any encounter potentially life-threatening. The power to inflict harm is greatly amplified with increased size. Additionally, these colossal insects would likely exhibit different social behaviors and ecological roles than their smaller counterparts. Many insects, such as ants and bees, rely heavily on teamwork and structured colonies. If these groups grew larger, their collective strength and organization might threaten human environments. Moreover, the alteration of food chains could have far-reaching effects, disrupting agriculture and local ecosystems. This could lead to resource scarcity, forcing humans to adapt rapidly to new environmental realities. In terms of survival, one of the biggest challenges would be defense. Standard pesticides and other control measures would likely be ineffective against larger insects, which could also develop new forms of resilience. Humans would need to look toward innovative solutions to manage and mitigate encounters. Strategies might involve advancements in technology or biology to find means of deterrence or containment. Lastly, the psychological implications could be profound. The fear and anxiety associated with encountering these enormous creatures could lead to social unrest or shifts in societal norms. Our relationship with nature would undoubtedly be tested, potentially forcing a re-evaluation of our coexistence with wildlife. The thought of navigating a world suddenly inhabited by enormous insects raises essential questions about adaptability, resilience, and our understanding of nature itself. Gigantism in insects presents a fascinating glimpse into how evolution can produce extraordinary adaptations. This phenomenon, often observed in certain prehistoric bugs, has captivated scientists trying to understand the underlying physiological changes responsible for such growth. Insects are unique creatures that rely on a process called passive diffusion to exchange gases directly through their exoskeletons. As their size increases, this method of oxygen intake becomes less efficient, which poses significant challenges for larger insects. To adapt to their increased size, giant insects require a more sophisticated respiratory system. Some of these colossal species developed specialized structures to enhance oxygen uptake. For instance, larger tracheal systems, akin to complex networks of tubes, allowed them to distribute oxygen more efficiently to their tissues. This structural adaptation is crucial because in larger bodies, cells that are farther from surface areas would otherwise struggle to get adequate oxygen to sustain metabolic activities. However, the size increase also led to escalated energy demands. A larger insect generally requires more energy to move and to maintain bodily functions than its smaller relatives. As a result, these giant insects had to adapt their feeding habits and nutritional intake to meet these demands. Some became opportunistic feeders, consuming a wide range of organic materials to maintain their energy levels, while others evolved enhanced digestive systems capable of breaking down tougher materials. Despite these adaptations, giant insects faced additional challenges, such as the increased risk of predation and vulnerabilities associated with their size. The dynamics of their ecosystems would have shifted as well, influencing their behavior and interactions. Overall, the physiology and energy requirements of these gigantic creatures illustrate an extraordinary chapter in the story of evolution, demonstrating both the triumphs and trials associated with size on such an immense scale. Throughout our planet's history, insects have reached astonishing sizes. Think of the dragonflies with wingspans stretching over 2 feet, or the colossal millipedes that roamed the Earth during the Carboniferous period. These impressive sizes raise questions about the anatomical features that allowed these massive insects to thrive in their environments. One of the key factors in supporting large body sizes in insects is their exoskeleton, composed primarily of a substance called chitin. This tough yet lightweight material provides structure and protection without being overly heavy. In larger insects, the exoskeleton is reinforced to withstand stress and support greater weight. Additionally, their bodies are often segmented, allowing for flexibility and movement without compromising strength. Respiration also plays a crucial role in the efficiency of these giant insects. Instead of lungs, insects utilize a system of tracheae, small tubes that deliver oxygen directly to their tissues. This direct delivery system becomes especially effective in larger insects, as it allows for a quicker exchange of gases. During periods when the atmosphere was richer in oxygen, such as the Carboniferous period, this respiratory system would have supported much larger sizes, as more oxygen could be absorbed to fuel their larger bodies. Furthermore, the muscular structure of these insects is uniquely adapted to their size. Large insects possess powerful muscles to operate their wings or legs efficiently, enabling flight or movement with relative ease. The combination of a lightweight yet robust exoskeleton, an effective respiratory system, and muscular adaptations allowed these ancient giants to not only survive, but thrive in a world that would be challenging for modern-day insects. This remarkable evolution showcases the adaptability of life, revealing how organisms can capitalize on their environments in unexpected ways. When we think about the diverse array of life forms on our planet, it's fascinating to consider how size influences the physiological traits of different species. Larger animals, often referred to as megafauna, typically exhibit distinct characteristics compared to their smaller counterparts. One of the most prominent differences lies in their metabolic rates. Generally, larger animals have slower metabolisms than smaller ones. This means that while they require more energy overall to sustain their size, they burn energy more slowly, which can lead to fewer required meals over time. Additionally, larger animals often possess adaptations that help them handle their bulk efficiently. For instance, many have developed more robust skeletal structures and stronger muscle systems to support their weight. Their respiratory and circulatory systems also reflect this size difference. Larger creatures may have more complex networks to ensure that oxygen and nutrients are effectively distributed throughout their bodies. Even in the realm of reproduction, size plays a significant role. Larger animals often have longer gestation periods and can produce fewer offspring, which reflects an evolutionary strategy of investing more in each individual rather than having many. Conversely, smaller animals typically exhibit higher metabolic rates, which often leads to quicker life cycles. They may grow and reproduce at a faster pace to counterbalance the higher energy demands of their smaller bodies. As a result, their physiological traits can lean towards rapid adaptation, allowing them to thrive in diverse environments. Smaller species might also occupy ecological niches that require more agility, leading to adaptations such as stronger limbs for climbing or lighter bodies for better maneuverability. In considering these dynamics, we see a clear interplay between size and survival strategies across the natural world. Whether it's the massive elephant moving gracefully through the savanna or the tiny hummingbird flitting from flower to flower, these physiological traits not only fulfill their immediate needs, but also reflect millions of years of evolutionary history, showcasing the incredible diversity of life on our planet. Giant insects, which roamed the Earth in the Paleozoic era, capture our imagination with their formidable size and unique adaptations. Some of these insects, such as the dragonfly-like Meganeura, had wingspans that reached almost 3 feet. Insects from this time thrived in a world much different from ours today, one where high oxygen levels allowed them to grow larger than anything we see among today's insects. Their body structures, designed to utilize the abundant oxygen, stand in contrast to the bulkier, warm-blooded mammals that would later dominate the planet. In contrast, creatures like the woolly mammoth and saber-toothed tiger represent a different evolutionary approach. Woolly mammoths, with their thick fur and massive tusks, adapted to the cold environments of the Ice Age. These mammals displayed complex behaviors and social structures, much like today's elephants. Saber-toothed tigers featured elongated canine teeth and robust bodies, enabling them to become formidable predators. While insects like Meganeura relied on size and flight for survival, these mammals developed intricate physiological adaptations to navigate their ecosystems. The challenges faced by these two categories of creatures also differed significantly. Giant insects experienced threats from environmental changes and competition with emerging vertebrates, whereas mammals had to contend with predators and climatic shifts during the Ice Ages. Their differing life cycles and metabolisms influence their resilience. Insects are cold-blooded and dependent on external temperatures, while mammals maintain their body temperature internally, allowing them greater range and adaptability in changing environments. Ultimately, the comparison between giant insects and massive prehistoric mammals highlights the diversity of life on Earth. Each group thrived in response to its own set of ecological pressures and opportunities. The story of life on our planet is shaped by such fascinating contrasts, revealing the intricate interplay of evolution that has led to the extraordinary array of species we observe today. Throughout the history of our planet, large prehistoric creatures such as dinosaurs, mammoths, and giant marine reptiles played significant ecological roles that were crucial for maintaining their ecosystems. These ancient beings were not just individual species. They formed intricate connections with one another and their environment, sharing responsibilities within their habitats. One of the primary roles these large animals held was that of herbivores or predators. The biggest herbivores, like the massive sauropods, consumed vast amounts of foliage, significantly shaping their landscapes. They helped control plant growth, facilitating a diverse environment that supported various other species. In turn, their large size and movement helped in the seed dispersal of numerous plant species, contributing to the ecological balance and diversity of their habitats. Predatory creatures, on the other hand, played an equally vital role in regulating prey populations. Large carnivores helped maintain the health of herbivore communities by ensuring that they did not overconsume vegetation. This balance prevented overgrazing and allowed for a healthier ecosystem, promoting biodiversity. Additionally, scavengers, which often included other large animals, would latch onto the remains of deceased creatures, thus recycling nutrients back into the soil and supporting new plant growth. Lastly, the interactions among large prehistoric species also influenced climate and geological processes. Their movements could alter landforms and sediment layers, helping shape the very ground we stand on today. All these interconnected roles emphasize the importance of these creatures in their ecosystems, creating a web of life that mirrors the complex ecological systems we see today. By understanding the ecological contributions of these magnificent giants, we gain deeper insight into the delicate balance of life on Earth, past and present. The study of giant creatures, both living and extinct, can offer fascinating insights into the biology and ecology of insects, particularly the larger species among them. When examining the ways in which these creatures have evolved and interacted with their environments, we can draw parallels to the adaptations and life cycles of big insects. For instance, the physiology of giant animals such as the giraffe or the elephant reveals a great deal about how size influences behavior, mobility, and feeding strategies, which is similarly relevant to larger insects like the Goliath beetle or the Titanus giganteus. One of the most intriguing connections lies in the concept of body size and its implications for metabolism, reproduction, and ecological niches. Research on giant land mammals shows that larger size can lead to longer lifespans and slower metabolism. This might inform our understanding of similarly large insects, suggesting that they may also benefit from a more gradual life cycle. Interestingly, the way that giant creatures dominate specific habitats can reveal how large insects might carve out their own ecological spaces, competing with or coexisting alongside smaller species. Furthermore, studying the structural adaptations in giant species can enhance our comprehension of biomechanics in larger insects. For example, the way in which large animals manage their weight and movement can shed light on how enormous insects maintain their structural integrity and navigate their environments. This perspective may help scientists understand why some insects evolved to be much larger than their typical counterparts, and what environmental factors contribute to this growth. Finally, understanding the extinction of many giant species due to climatic shifts and human activity lends urgency to the ongoing study of the planet's biodiversity. It emphasizes the importance of what we might lose if we do not protect even the smallest of creatures. Every species plays a role in its environment, and learning from the past helps guide conservation efforts today, ensuring that both giant creatures and insects continue to thrive in their ecosystems. Giant insects once roamed the Earth, dominating the skies and forests during the Carboniferous and Permian periods. Some of these massive creatures, like the dragonfly-like Meganeura, had wingspans stretching more than 2 feet. Their size was not just a fascinating feature, it had profound implications for the ecosystems they inhabited, particularly regarding nutrient cycling and decomposition. As these large insects lived and died, they played a crucial role in breaking down organic matter. Like today's insects, the giants of ancient eras fed on decaying plant material and other organic matter, accelerating the decomposition process. Their interactions with the ecosystem helped recycle nutrients back into the soil, enriching it and promoting plant growth. This process was vital during a time when Earth's atmosphere was rich in oxygen, allowing for such impressive sizes and robust ecosystems. In addition to their role as decomposers, giant insects facilitated nutrient cycling through their predatory behaviors. Larger forms of insects were part of a complex food web, preying on smaller organisms and themselves becoming prey for larger animals. This intricate network ensured that energy and nutrients were exchanged frequently within their environment. By influencing population dynamics, they contributed to maintaining a balance in their ecosystems, ensuring that no single species dominated. Moreover, giant insects also affected the movement and distribution of seeds and spores. Their feeding habits and life cycles helped to spread these crucial elements across vast distances. While they may no longer exist, their legacy continues to inform our understanding of how insects contribute to nutrient cycling in modern ecosystems, deepening our appreciation for the intricate relationships that sustain life on our planet. Understanding these prehistoric giants gives us insight into the crucial environmental roles even the smallest creatures play in our ecosystems today. In the vast tapestry of life on Earth, symbiotic relationships play a pivotal role in the survival and flourishing of various species. Insects, in particular, have a wealth of interactions with other organisms, some of which are mutually beneficial, while others may resemble more of a parasitic arrangement. These associations contribute significantly to our ecosystems, influencing everything from pollination to pest control. One striking example of such a symbiotic relationship is that between certain insects, like bees, and flowering plants. The bees gather nectar for food while simultaneously transferring pollen from one flower to another. This transfer is essential for plant reproduction, allowing flowering plants to produce seeds. In this case, both parties thrive. Bees receive a food source, while plants achieve successful pollination, highlighting the interconnectedness of life on our planet. Another fascinating relationship involves ants and aphids. Aphids produce a sugary substance called honeydew, which ants find highly palatable. In return, ants protect aphids from their natural predators, such as ladybugs. This mutual protection ensures that aphids can continue to feed and reproduce, while ants secure a reliable food source. Such intricate relationships reveal the complex social structures and interdependencies found in nature. Some insects also engage in relationships that may be considered parasitic. For instance, certain types of wasps lay their eggs within or on the bodies of other insects. When the wasp larvae hatch, they consume the host from the inside out. While this may sound harsh, it is a reminder of the diverse survival strategies employed by different species in the struggle for life. Understanding these varied symbiotic relationships underscores the intricate web of life, where cooperation and competition coexist, ultimately shaping the biological community around us. Throughout Earth's history, insects have played a crucial role in shaping ecosystems, but in the age of giants, their influence was particularly profound. During the Carboniferous period, roughly 300 million years ago, insects grew to impressive sizes, in part due to the abundant oxygen in the atmosphere. This combination of size and environmental conditions allowed these giant insects to exploit resources that smaller insects could not, ultimately leading to the development of new ecological niches. Giant insects, such as dragonflies with wingspans reaching up to 2 feet, were formidable predators. Their size not only made them effective hunters, but also altered local food webs significantly. They preyed on various smaller animals and competed with other predators, prompting evolutionary adaptations in both prey and competitors. As these insects influenced the dynamics of their environment, new relationships developed, allowing for a diversity of species to find their own roles within the ecosystem. Moreover, the presence of these large insects impacted plant life as well. Pollination, decomposition, and seed dispersal were all affected by their size and behavior. For instance, giant herbivorous insects played a vital role in consuming and breaking down plant material, which facilitated nutrient cycling in the soil. This activity encouraged the growth of certain plant species that could thrive under these new ecological conditions, leading to an expanded variety of flora. The interactions of giant insects with their environments catalyzed the formation of new ecological niches, enriching biodiversity. As these insects shaped their habitats, they allowed for the rise of different ecological roles, ultimately contributing to the complexity of ecosystems that would continue to evolve long after the era of giants had passed. These interactions exemplify the delicate balance of nature, demonstrating how even small changes in one aspect of the environment can lead to significant shifts across an entire ecosystem. Giant insects have intrigued scientists and the public alike for centuries. These incredible creatures, which include prehistoric species such as Meganeura, a massive dragonfly with a wingspan of nearly 2.5 feet, raise intriguing questions about evolution, environment, and extinction. One of the most pressing unsolved mysteries is why insects grew to such large sizes during the Carboniferous period, about 300 million years ago. At that time, Earth's atmosphere had significantly higher oxygen levels, which likely allowed insects to grow larger than their present-day relatives. However, what exactly triggered this impressive size increase remains a topic of debate among experts. Another enigma revolves around the limitations of size for insects today. Modern insects, such as beetles and moths, exhibit a range of sizes, but tend to be considerably smaller than their ancient counterparts. Various factors may contribute to this phenomenon, including respiratory systems that rely on diffusion to deliver oxygen, as well as predation pressure and environmental changes over millions of years. Researchers grapple with the question of whether there were specific ecological pressures that restricted the growth potential of insects in contemporary ecosystems. The fossil record provides tantalizing glimpses into the past, yet it remains incomplete. Many large insects have been discovered, but we still do not fully understand the ecological roles and behaviors of these ancient giants. How did they hunt or evade predators? Did they share their habitats with equally impressive arachnids, or were they the undisputed rulers of the skies? As scientists continue to analyze fossilized remains, the answers to these questions could reshape our understanding of prehistoric ecosystems. Lastly, the possibility of modern-day giant insects is becoming an increasingly popular topic of speculation. Could environmental changes, such as global warming or shifts in atmospheric conditions, ever lead to insects regaining some of their prehistoric size? While these ideas remain largely in the realm of science fiction, they ignite our imagination and underscore the fragility of ecological balance. The mysteries surrounding giant insects remain a captivating frontier in the world of biology, beckoning researchers and enthusiasts alike to explore further. The debates surrounding the extinction and evolution of species are as complex as they are fascinating. Scientists constantly engage in discussions about the various trajectories that life on Earth has taken and how certain species have thrived while others have vanished. One of the key aspects of these debates involves understanding the mechanisms of extinction. While many scholars point to catastrophic events such as asteroid impacts or volcanic eruptions, others highlight the role of gradual environmental changes like climate shifts or habitat destruction in leading to a species' demise. Additionally, the evolution of species is deeply intertwined with these extinction narratives. Some scientists explore how evolving traits can either help a species survive or contribute to its extinction. For instance, adaptive evolution might enable a species to exploit new ecological niches or develop resistance to diseases. Conversely, traits that were once beneficial might become liabilities in the face of sudden environmental changes. This leads to questions about whether certain evolutionary advantages could actually be detrimental when circumstances shift dramatically. Another layer to these debates involves the concept of mass extinctions in Earth's history. The fossil record reveals 5 major events where a substantial percentage of the planet's species went extinct in relatively short geological timescales. Each of these events has spurred a wealth of research about the drivers behind them. Some scientists argue that human activity could be leading to a sixth mass extinction, likening modern biodiversity loss to past catastrophic events. This prompts critical conversations about anthropogenic factors and their long-term impact on the planet's ecosystems. Moreover, advancements in genetic and environmental science are sparking new discussions. The study of ancient DNA has provided insights into the evolutionary history of species, revealing how they adapted to past climate changes. In this context, scientists are re-evaluating extinction events by considering the resilience and vulnerability of species through various environmental challenges. These multifaceted debates enrich our understanding of life's history on Earth, reminding us that evolution is not a linear journey, but a complex interplay of survival, adaptation, and often loss. The world of prehistoric giants, from the towering dinosaurs to colossal mammoths, continually captures our imagination. Our current understanding of these magnificent creatures is based on fossil records, comparative anatomy, and the study of their environments. However, each new discovery can shift our perceptions significantly, revealing complexities we have yet to fathom. Future discoveries hold the potential to fundamentally reshape our understanding not only of these animals themselves, but also the ecosystems they inhabited. New fossil finds can shed light on species diversity and evolutionary relationships. For instance, a discovered fossil might reveal a previously unknown species or suggest that known species had different behaviors or life cycles than we assumed. The advances in technology, such as high-resolution imaging and molecular analysis, allow scientists to examine fossils in greater detail than ever before. This can lead to new insights about how these giants lived, what they ate, and how they interacted with one another and their environment. Moreover, advancements in genetic analysis could help reconstruct the appearance and functions of extinct species more accurately. Techniques such as ancient DNA extraction may enable researchers to understand how dinosaurs may have communicated or how mammoths adapted to their icy habitats. Such revelations could unlock vital information about the evolutionary pressures these animals faced, mapping out their adaptations and survival strategies through changing climates. Lastly, as we explore previously untapped regions of the Earth, we may uncover new fossil sites that challenge our existing narratives. The discovery of a unique ecosystem, for example, could suggest that these giants coexisted with different life forms and influenced their development. Every artifact unearthed and each piece of data collected could deepen our understanding of prehistoric life, allowing us to appreciate the intricate tapestry of existence that defined the ages of these ancient behemoths. With each find, the story of our planet's history grows richer and more nuanced, leaving us in awe of the complexity of life that once roamed our Earth. Understanding giant insects captures the imagination and offers a powerful way to engage the public with the fields of paleontology and geology. These colossal creatures, many of which roamed the Earth hundreds of millions of years ago, not only fascinate through their sheer size, but also provide critical insights into ancient ecosystems. When we consider that some insects could grow as large as birds, it challenges our preconceived notions of biology and evolution, prompting deeper inquiries into how environmental conditions shape life. Moreover, these immense insects serve as important indicators of past climates and atmospheric conditions. Fossils of giant insects tell a story about an era when the Earth had higher oxygen levels and different ecosystems, sparking curiosity about the interplay between environment and evolution. Engaging with these intriguing relics encourages the public to explore how life adapts and evolves in response to changing Earth conditions. This can stimulate discussions about contemporary issues, such as climate change and biodiversity loss, linking our current concerns with those of the past. Additionally, the exploration of giant insects promotes broader interest in paleontological studies. Schools, museums, and public lectures often feature these creatures in their displays and educational programs, making science accessible and exciting. This approach can spark a desire for further understanding and encourage younger generations to pursue careers in science, technology, engineering, and mathematics, or what we commonly refer to as STEM fields. Engaging with giant insects creates an accessible entry point into the world of fossils and geological history that resonates with people of all ages. The surprising fact that these ancient beings once thrived on our planet evokes a sense of wonder, inviting everyone to marvel at life's diverse forms and the Earth's extensive history. In this way, the study of giant insects not only enhances the public's understanding of paleontology and geology, but also deepens our connection to the evolutionary narrative of life on Earth. Museums and educational institutions serve as vital guardians of the legacy of giant insects, weaving a narrative that connects the past with our present understanding of evolution, biology, and the environment. These institutions house extensive collections of fossils, models, and cast replicas, showcasing the incredible diversity and scale of insects that once roamed our planet. Through scientific research and curation, museums provide a framework for understanding how these ancient creatures thrived, their adaptations, and the ecosystems they inhabited. Educational programs developed by these institutions play an essential role in captivating the interest of students and the broader community. By presenting exhibitions that highlight the size and significance of giant insects, museums can ignite curiosity and engage audiences of all ages. Interactive displays and guided tours enrich the learning experience, encouraging visitors to ponder questions about climate, natural selection, and the interconnectedness of life forms throughout Earth's history. Furthermore, these institutions contribute to ongoing research in entomology and paleontology, advancing our knowledge about the factors that led to the enormous sizes of prehistoric insects. Scientists study fossilized remains to glean insights into atmospheric conditions such as oxygen levels, which may have supported the existence of these giants. This collaboration between educational institutions and researchers not only preserves the past, but helps predict the future implications of climate change on current insect populations. Ultimately, museums and educational organizations are vital, both as places of preservation and as platforms for education. They foster a deeper appreciation for biodiversity and ecological balance, reminding us that the world of insects, whether large or small, has an immeasurable impact on our environment. Their efforts ensure that the remarkable legacy of these colossal creatures continues to inspire and educate future generations. Documentaries serve as powerful tools for educating audiences about prehistoric life by weaving together compelling visuals, expert insights, and engaging storytelling. Through stunning reconstructions of ancient environments, viewers can immerse themselves in the landscapes where dinosaurs roamed or ancient mammals flourished. These visual representations bring to life scenes that are often unimaginable, sparking curiosity and wonder about the world that existed millions of years ago. In addition to visuals, documentaries often feature expert interviews with paleontologists and geologists who explain complex concepts in an approachable manner. Their passionate narratives provide context to the findings, helping audiences understand not just what these creatures looked like, but also how they lived, interacted, and evolved over time. This connection to human curiosity about life's origins ignites a deeper appreciation for the history of our planet. Another effective technique employed by documentaries is storytelling that emphasizes the drama of survival, adaptation, and extinction. By highlighting the challenges faced by prehistoric creatures and the evolutionary triumphs they achieved, these films create relatable emotions. This storytelling approach can foster a sense of connection between viewers and the ancient beings that inhabited the Earth, transforming mere facts into a narrative that resonates on a personal level. Finally, documentaries can inspire interest in preservation and the ongoing study of our past. By illustrating how studying prehistoric life informs our understanding of biodiversity and environmental change, these films encourage audiences to engage with current scientific efforts. Thus, documentaries not only educate but also inspire a commitment to exploring the past and its relevance to our future. The history of giant insects provides a captivating glimpse into the intricate relationship between Earth's environment and biodiversity. During the Carboniferous period, roughly 300 million years ago, insects grew to sizes that seem almost fantastical by today's standards. Fossils reveal dragonflies with wingspans up to 2 feet and colossal millipedes that spanned nearly 8 feet. This astonishing size can be attributed to the high levels of oxygen in the atmosphere during that era, which reached around 35% compared to the 21% we breathe today. Such elevated oxygen levels allowed insects to grow larger, as their respiratory systems, which rely on passive diffusion, could efficiently deliver oxygen to their bodies. As we look deeper into Earth's geological past, we find that similar episodes of increased biodiversity coincided with specific environmental conditions. The abundance of lush vegetation during the Carboniferous created an ideal habitat for these giant insects. Warm temperatures and ample food sources fostered thriving ecosystems where diverse species could flourish. This period marked a significant stage in evolutionary development, demonstrating that the interplay between atmospheric conditions and biological growth can lead to remarkable diversity. However, the world we inhabit today presents different challenges and opportunities for biodiversity. Oxygen levels are lower, and human impact through habitat destruction and climate change poses threats to many species. Yet, examining the history of these prehistoric giants underlines the resilience and adaptability of life. It paints a picture of how species evolve in response to their environments, often exhibiting extraordinary capabilities in extreme conditions. Ultimately, the tale of giant insects serves as a reminder of our planet's dynamic and shifting nature. As we strive to understand our current biodiversity and the challenges it faces, the history of these ancient creatures encourages us to appreciate the delicate balance of ecosystems and the conditions that sustain diverse and thriving life on Earth. Understanding these connections is crucial as we look to the future and work to protect the intricate web of life that exists today. The life cycles of giant insects offer fascinating parallels to the broader patterns of rise and fall seen across various species. These enormous insects, like certain dragonflies or millipedes, typically undergo complex life stages that involve both aquatic and terrestrial environments. This transformation mirrors the life cycles of many species, which often include stages of growth, development, and eventual decline due to environmental changes or competition for resources. Insects like the giant dragonfly, which thrived during the Carboniferous period, reached impressive sizes due to abundant oxygen levels and vast, swampy environments. During this period, the Earth's climate and atmospheric conditions fostered the growth of these large insects. Their rise can be attributed not only to their adaptability, but also to the ecological niches they occupied, similar to the way different species flourish under specific conditions. When external factors shifted, such as a decrease in oxygen levels or significant climatic changes, these giant insects struggled to survive, reflecting the inevitable decline seen in many organisms that depended on a stable environment. As we think about the rise and fall of giant insects, it highlights a broader ecological truth, the delicate balance between species and their environments. For instance, when competition intensifies or when new predators enter the scene, even the most successful species can face significant challenges. Many once prominent species have vanished as a direct result of these shifts. The giant insects serve as a poignant reminder of how life on Earth is often interconnected and susceptible to external pressures, a theme that resonates throughout the history of life itself. Ultimately, the life cycles of giant insects encapsulate the idea of adaptation and survival in the face of changing environments. Their existence underscores the importance of understanding ecological dynamics and the consequences of shifts within ecosystems. Whether it is the thriving giant insects of the past or the more diminutive varieties we see today, These life cycles reflect the ongoing story of life's resilience and vulnerability in an ever-changing world. The existence and eventual extinction of various species throughout Earth's history offer profound insights into the sustainability and resilience of contemporary ecosystems. Each extinction event, from the mass extinction of dinosaurs to the gradual decline of countless lesser-known species, serves as a stark reminder of the fragility of life and the intricate balance within ecosystems. These events often result from various factors, including climate change, habitat destruction, and shifts in the food web. By studying these historical occurrences, we can glean important lessons for our modern environment. One key takeaway is the role of adaptability. Species that thrived in the face of changing conditions often possessed unique traits that enabled them to cope with new challenges. For example, the mammals that survived the extinction of the dinosaurs were able to adapt to diverse and rapidly changing environments. As we face unprecedented climate shifts today, understanding the mechanisms of adaptability becomes crucial. Contemporary biodiversity may be our best ally in ensuring the resilience of ecosystems, as a wide array of species can provide stability and support through their various interactions. Another significant lesson revolves around the impact of human activity on natural habitats. The wild transformations driven by industrialization, urbanization, and agricultural expansion mirror past extinctions that were often triggered by dramatic environmental changes. By examining the consequences of our actions on biodiversity, we can recognize the urgent need for conservation efforts. Preventing habitat loss and preserving ecological niches are vital steps in avoiding the pitfalls faced by many ancient species, allowing ecosystems to thrive rather than collapse. Lastly, the interconnectedness of all life emphasizes the importance of a holistic approach to ecosystem management. Each species, no matter how small, plays a role in its ecological niche. The extinction of one species can trigger a domino effect, harming others and compromising the health of the entire ecosystem. Learning from the past, we must strive to protect not only charismatic megafauna, but also less visible, but equally important organisms. In doing so, we can work towards a sustainable future that honors the delicate balance observed in nature for millions of years. Throughout history, various cultures have interpreted and mythologized giant insects in fascinating and diverse ways. In ancient civilizations, these creatures often took on symbolic meanings, representing both fear and awe. For example, in several Mesoamerican cultures, such as the Aztecs and Maya, insects were not just pests, but powerful creatures linked to deities and the afterlife. The jaguar warrior, associated with strength and ferocity, was sometimes depicted with attributes of insects to signify dominance over both the earthly and celestial realms. In ancient Egypt, the scarab beetle emerged as a powerful symbol of regeneration and rebirth. This beetle was revered as a manifestation of the sun god Ra, rolling the sun across the sky, much like it rolled dung across the earth. Figures of scarabs were often placed in tombs to symbolize the journey into the afterlife, representing transformation and eternal life. This connection between giant insects and spiritual significance illustrates how important these creatures were in the mythological frameworks of many ancient cultures. In contrast, cultures in East Asia have often portrayed insects as embodiments of resilience and industriousness. The giant silk moth, for instance, symbolizes not just the fabric produced from it, but also patience and perseverance in the context of life's challenges. Similarly, the effectiveness of ants in collaboration within their colonies is often exalted, seen as a model for human society and cooperation. These interpretations highlight a blend of reverence and practicality, shaping how insects influence cultural narratives. Modern interpretations and pop culture have also taken an interest in these larger-than-life insects, often portraying them as harbingers of environmental warnings or threats. The frequency of giant insect imagery in movies and literature, such as science fiction and horror genres, reflects a deep cultural fascination with the unknown or the unexplained. This ongoing fascination represents both a respect for the prowess of the natural world and an exploration of the fears inherent in humanity's relationship with nature. This interplay of fear, reverence, and symbolism continues to shape our understanding of these fascinating creatures in contemporary society. Throughout history, artists and storytellers have depicted mythical creatures in a multitude of fascinating ways, weaving them into the fabric of human culture. From ancient cave paintings to contemporary literature, these beings have served as symbols of our fears, dreams, and the mysteries of the natural world. Creatures such as dragons, unicorns, and mermaids often reflect the human experience, embodying both our aspirations and our anxieties. These depictions offer insights not just into the creatures themselves, but also into the societies that imagined them. In the realm of visual art, mythical beings have often been portrayed with vivid imagination and striking detail. For example, famous painters like Hieronymus Bosch created intricate depictions of fantastical creatures in his renowned works, which sparked curiosity and fear. Such vivid imagery captures the essence of these creatures, often depicting them in the context of lessons about morality and the human condition. Similarly, illustrations in ancient manuscripts and folklore frequently showcase these beings as guardians, tricksters, or embodiments of nature's wild essence, stimulating both wonder and contemplation. Storytelling traditions across various cultures have also played a critical role in shaping the narratives surrounding these creatures. In epic tales, such as those of the ancient Greeks and their myths about centaurs or sirens, these beings often serve to challenge heroes, test virtues, or illustrate deep moral lessons. Modern literature, from classic fairy tales to contemporary fantasy novels, also continues this tradition, allowing for complex characters and rich story arcs that allow us to connect with these mythical beings. Works like The Hobbit or Harry Potter not only bring these creatures to life, but also explore themes of friendship, courage, and the battle between good and evil. Moreover, these artistic and narrative representations evolve with society's changing views and values. For instance, where dragons were once solely depicted as fearsome beasts to be slain, modern storytelling often presents them as misunderstood allies or intelligent beings. This shift mirrors a broader trend in storytelling where empathy and understanding become central themes. As we continue to engage with these enchanting creatures through various forms of art, they will invariably remain a dynamic reflection of our shared humanity, revealing how we perceive and interact with the world around us. Giant insects have long captured the human imagination, melding science fiction with the natural world in a way that both fascinates and terrifies. It's our innate curiosity about the unknown, intertwined with the primal fear of creatures that can outsize us, that fuels a recurring theme in storytelling. From classic literature to contemporary cinema, the portrayal of colossal insects often serves as a metaphor for human fears, societal issues, or environmental concerns. One prominent example is the iconic movie The Fly, where the transformation of a human into a giant insect serves as a poignant commentary on the dangers of unchecked scientific exploration. This narrative not only taps into our fear of losing control, but also reflects the anxieties surrounding technology and its impact on humanity. Similarly, films like Them and The Mist depict giant insects as symbols of nature's retaliation against human hubris, prompting audiences to ponder the consequences of our actions on the ecosystem. In addition to horror and science fiction, giant insects find a place in the realm of fantasy. From the colossal spiders in J.R.R. Tolkien's The Hobbit to the swarming army of ants in the animated film A Bug's Life, these creatures often signify transformation, adventure, or the idea that even the smallest beings can wield immense power. This versatility allows them to occupy various narrative roles, from villains to reluctant heroes, making them a useful tool for storytellers aiming to explore complex themes of morality, growth, and survival. Furthermore, the portrayal of giant insects has influenced popular culture and shaped media representations beyond film and literature. Video games, cartoons, and merchandise often leverage these massive creatures to attract audiences, solidifying their place in collective memory. So, next time you encounter a giant insect in a story or on-screen, remember that these creatures are not just products of imagination. They are reflections of our deepest fears, dreams, and the fascinating world that continues to inspire us. The study of giant insects opens a fascinating window into the past, revealing broad themes that speak to evolutionary biology, environmental changes, and the limits of life on Earth. One significant theme is the relationship between the size of organisms and the atmospheric conditions they inhabit. During the Carboniferous period, roughly 300 million years ago, oxygen levels were considerably higher than today, reaching up to 35%. This abundance of oxygen allowed insects to grow much larger than their modern counterparts. The more oxygen an insect can take in through its exoskeleton, the larger it can grow. With increased oxygen, some insects evolved to the size of small birds, like the dragonfly-like Meganeura, boasting a wingspan of up to 2.5 feet. Another theme that emerges is the impact of ecological niches on insect development. Giant insects thrived in lush, swampy environments rich with vegetation, allowing them to develop unique adaptations, such as larger body sizes to compete for food or evade predators. The existence of giant insects also provides insight into predator-prey dynamics and competition among species. As ecosystems evolved, these dynamics shifted, eventually leading to the extinction of many of these colossal species, a testament to how interconnected life on Earth is and how environmental factors determine the survival of creatures. A third theme relates to the concept of evolutionary pressure. The fossil record shows that, as the climate changed and oxygen levels decreased, these giant insects could no longer sustain their size. New predators emerged, and with the transformation of habitats, their advantages dwindled. This illustrates a critical lesson in evolutionary science. That size alone does not guarantee survival. Adaptation, resilience, and the ability to thrive within changing conditions play vital roles in the long-term survival of any species. Lastly, the study of giant insects serves as a fascinating reminder of the limits of life. While some species thrived in previous epochs with different environmental conditions, modern ecosystems present their own challenges. Ecological balance is vital, and changes in climate can have dramatic effects on even our smallest inhabitants. The history of giant insects is not just a story of size, but also a narrative about adaptability, extinction, and the enduring influence of Earth's changing environments. This complex tapestry of life continues to inspire curiosity and wonder about the ancient world and its connection to the ecosystems we know today. As we navigate the complexities of today's scientific and environmental challenges, ancient themes of interconnectedness and sustainability offer valuable insights. Many cultures have long understood the delicate balance that exists within ecosystems. By recognizing that all components of nature are linked, we can adopt a holistic approach to problem solving. This perspective encourages collaboration among various fields, scientists, policymakers, and communities, empowering us to tackle issues like climate change, pollution, and biodiversity loss more effectively. The theme of stewardship, often found in indigenous philosophies, emphasizes the responsibility we have to care for our planet. This principle can guide current conservation efforts and lead to more responsible resource management. By viewing ourselves as caretakers rather than mere users of natural resources, we foster a sense of duty that can inspire innovative strategies for sustainable development. This mindset shift is vital when addressing the overconsumption and waste that threaten our environment. Furthermore, the historical context of resilience teaches us valuable lessons about adaptation in the face of adversity. Just as species evolve to survive changing conditions, humans must embrace adaptability in our technological and social approaches to environmental issues. Scientific advancements can aid in creating resilient infrastructures, developing renewable energy sources, and implementing efficient waste management systems that align with the needs of our planet. Ultimately, applying these themes encourages a more profound sense of responsibility and innovation in how we approach current challenges. By looking to the past for guidance and inspiration, we can forge a future where scientific inquiry and environmental integrity coexist harmoniously. As we cultivate an appreciation for our connection to the Earth, we become more equipped to face the pressing issues of our time. The story of giant insects on our planet is a captivating chapter in Earth's natural history, filled with clues about evolution, environmental changes, and ecological dynamics. To deepen our understanding of these fascinating creatures, future research could focus on several key directions. One critical area is the exploration of fossil records. By examining well-preserved specimens in sedimentary deposits, scientists can piece together the morphological variety and ecological roles of these giants, learning how they adapted to their environments and coexisted with other species. Another promising line of inquiry is the study of the environmental conditions that allowed insects to reach such large sizes. During the Carboniferous period, oxygen levels in the atmosphere were significantly higher than today. Researchers could investigate how variations in atmospheric composition throughout Earth's history influenced insect size and diversity. By modeling ancient climates and ecosystems, scientists can better understand the dynamic interplay between environmental factors and biological evolution. Genetic analysis also holds the key to unlocking the mysteries of giant insects. By comparing the genomes of modern insects with those of their prehistoric ancestors, researchers could identify the genetic adaptations that enabled larger body sizes. This genetic research may also reveal insights into growth mechanisms and metabolic processes, enhancing our comprehension of how size evolution occurs across different species. Finally, studying the interactions between giant insects and their ecosystems can provide valuable lessons. Understanding their role as predators, prey, and competitors helps reconstruct ancient food webs. This could inform current ecological studies and conservation efforts, as the lessons learned from the past can guide our approach to preserving biodiversity today. Through these avenues of research, we can continue to illuminate the remarkable saga of giant insects and their lasting impact on Earth's natural history.